What's good, everybody? Happy Thursday. And it looks like my camera is frozen. 1 second. I don't know why it's frozen, but it's okay. We'll figure this out without having to move this. Sometimes it just be happening that way. Let's see. How's everyone doing? Can you all actually hear me? I think you can hear me. Let me fix my camera. Let's see, which one is it? Sony cam off, on. Nope, I gotta actually change it to something like this, and then change it back to the 4K. Man, sometimes this OBS thing be messing me up. But what's up, everyone? Now I am in fact back. Yes, and I was in fact a ventriloquist right there. But what's up, everyone? What's up, rollers? Congratulations on being first. Sin City, I was looking for your GitHub repo conduit microservices but couldn't find it. Yes, because now it is it's broken up into microservices now, so there's no microservices one. If you go to my GitHub and you type in conduit, you should see front end, back end, and Nginx right now. Soon there will be a fourth, which will be Mongo. But yes, there are three different services now. We are operating in the poly repo paradigm now, and not the mono repo. So yes. What's up, you Unjaded? How you doing, Unjaded? Zamuro 89, welcome. EQ Explorer. What's up, Ball Bearded Builder? How are you doing today? First off, shout out to you. Let's see. Let me get the shout out on my other keyboard over here. I'm gonna get my setup going. It's gonna be Bald Bearded Builder. It's weird typing over to the side, but please go give Bald Bearded Builder a follow. Does some pretty cool stuff here on Twitch. What's up, MTDVP? How are you doing? What about the Docker Compose file? That's the phenomenal question about the Docker Compose file. The Docker Compose file exists on the server. Yes, that's a good question. We'll get that. We'll have to move that somewhere. I can upload it before we're done here. Remind me close to the end. Yes, I see we've got a little F print statement here, a formatted print. Hello world, I love it. How you doing? Even though we don't know what world is. Let's see. Okay, so what's up, A? How you doing tonight? So tonight, what we are doing is we will be learning all about Hashtable. So this is the first of data structures week, and this is just the week to kind of get started off with data structures. So last time we did linked lists, we talked about arrays, we did linked lists, we did queues, and we did stacks, and so we were able to get through most of that. We spent most of the time on linked lists, because once you get that, stacks and queues are relatively simple in comparison. But tonight we are only going to be focusing on hash tables. Why only focusing on hash tables? Because hash tables take a little bit longer to implement, and I want us to take some time to focus on them, especially since we are moving into solving some searching and sorting algorithms in the next 2 weeks, where we will actually be introduced to some new data structure, so that we don't have to rush through this evening. There are no slides tonight. I'm going to be drawing everything, so we'll see how we're going to try this out. There are slides for this, but I'm going to try drawing out everything and then providing those as slides at the end for anyone watching afterwards. But yeah, so we're just gonna be focusing on hash tables tonight. There's a number of things to learn in this in this tonight. It's going to be good. We're gonna take our time. And we're gonna get through it. I have only done, it's really funny, I was talking to someone earlier and I was like, I set up this curriculum a little while ago, and I've done hash tables before. I've done them mostly in Python is the most times I've implemented them. That's usually my go-to. Like if I were gonna go to a coding interview and they were gonna ask me to implement a hash table, I would actually do it in Python just because I'm most familiar with that. I was like, have I ever implemented one in Go? And then I rushed to try to implement one in Go earlier today, and so I was successful, and then actually after I implemented my own, I went around and looked around to see some other implementations and Go to kind of see some good stuff, and I think I have a good I'm hoping I can recreate what it has of notes. But again, just like always, I really don't like doing the cookie cutter, hey, here's the end product, let's go through it. I think working through it and seeing what it becomes is great, and then we'll compare it maybe to one of the cookie cutter answers a little bit later. So let's see, where are we at first? No, we want to go to, oh, so I did change my background first off. Oh, I knew I had an announcement. The announcement, this is a pretty small announcement. And only a few of you are going to care, but remember how I kept saying I was having issues? Like, you know, we got my computer worked out to where it wasn't shutting down anymore and stuff. Power supply issue, great. But I noted that there were still some performance issues that I had always been seeing in a couple games, Call of Duty to be very specific, low frame rates and stuff with a pretty powerful computer. We discovered the problem. The problem was actually memory speeds. So I knew about Ryzen. I have a Ryzen CPU. Ryzen really likes fast memory. I knew that when I built it. I bought 3600 megahertz memory. All right. But yesterday I discovered that my memory was not running at 3600 megahertz. It was only running at 2133. So I was losing a lot of speed. This was due to a setting in the BIOS. Went and updated that setting in the BIOS. And voila, I'm now able to finally run my games at 144 hertz. Yes, I did in fact forget XMP, for sure. I thought, well, yes, I forgot XMP. Well, I didn't forget it. There was a default profile which was basically off, and I had to like enable like a real profile. But yes, that was it. And that gave me significant performance increases. My computer seems a lot snappier now as well. So, you know, almost a whole year with my computer working at partial capacity, but now we finally work those things out. But cool, some OSD monitoring tools. Yeah, I'm now that I'm back in Windows more than I was, I'm actually gonna dive into Windows a little bit more and start learning how to do all the cool stuff. But let's head over straight into the whiteboard, which you can, there we go, straight into the whiteboard, which you can now see. And we're going to use this as much as we can this evening. So tonight's plan is, wait, the whiteboard, why is it still, is it, did I remove it? Wait, can you see this? Oh yeah, okay. It's just weird in the way that it updates. All right, so tonight we are going to learn a little bit about hash tables. Now we're gonna learn, we're gonna have to touch on a couple of different things tonight for hash tables. We are going to have to dive into the best way to do this is to do some recursion in here. There's gonna be a little bit of recursion, small amount of recursion, so we'll talk about when we get there. But let's talk about what hash tables are. So hash tables, very common data structure, very important data structure, one that there was a period of time where I wanted to go try to be a software engineer, to spend some time as a software engineer. I'm still actually upset I didn't get to go do that, to go be a software engineer for a little while at a company, even though I ran the software engineering teams. But it would have been cool to just purely do software stuff all day. But this is probably, at all the algorithmic things that I was asked to do, hash tables are probably the most frequent I was asked to do. So it's a very good one to learn. That's why we're going to spend the entire day on it. But what are they? Well, imagine, we've learned about arrays, we've learned about our lists and things, we learned about how arrays work last time and those linked lists. But imagine you have, you know, we've been working with very small ones of these, very small arrays, very small lists. But imagine your list is very long, all the way out here, very, very, very long, lots of spaces, you know, tons and tons of spaces all the way out to the end. Great. Our computer has enough memory, it can hold this stuff, no problem. All these things get filled, phenomenal. But what if you have to do some type of problem where you have to find something in this array, but you don't know where it is? And so you could, you know, begin to iterate through, and you can say, cool, I want to look for something. And this is my that's my hourglass. I mean, not my hourglass, my magnifying glass. That's my detective glass right there. And so you go and look at the first one and you say yes or no, and it says nope. And then you move over to the next one. You say yes or no, you say nope, and you just keep moving over. Keep moving over, keep moving over, keep moving over until you actually find what you were looking for. Okay, so let's say we were, you know, over here, let's say we were looking for the name Aaron. And, you know, I'm full of myself, so I use my name in all these examples. And, you know, let's say all these are filled. It's going to keep going over, and it's going to compare Aaron to whatever is in each of these every time, and it's just going to keep moving over until it finds it. That works. Absolutely, but it can take a very long time to do if this gets really long. And so we talked about big O notation in the first part of this course. And just to give you just a slight, we're not going to go back over it deeply. It's definitely something I think you should check out. But we are going to talk about it a little bit more as we get into sorting and searching in the next 2 weeks, because it is important. But the big O notation just describes time complexity and basically how changes in an application are going to respond to how long it takes to solve it. And so this will because of the big O notation for this, because of the complexity for this is it's basically a constant solvable problem. And you know, the more and more we add to this list, the longer and longer it will take to solve the problem. So it can be pretty slow for this to happen. And again, imagine you have hundreds of thousands, millions of things in an array like this. And so hash tables give us a method for looking up data in these arrays. They give us a method for looking up data in an array by knowing exactly where it is. So an array is, let's see, can I move this up? I'm going to try to save all of these. I don't really know how to use this whiteboard. Don't export. Let's see. How can I? There we go. Because now I can export all of this all at once. What's up, silly boy? How you doing today? How are you doing, Paul Blart Mall Cop? I haven't seen you here in a while. It's good to see you. It's good to have you here. So, that array, these things are indexed. So we have, you know, draw a big box here. 1, 2, 3, 4. Okay, so this, let's say, you know, let's say the number 6 is in here, the number 25 is here, 83 and 12 and 47. Right, 0 index though. This is an array. And this is in the 0 spot, the 1 spot, 2, 3, 4. So we can reference each of these things by their number. Oh, I appreciate that. This is day 2 of the shirts. You know, I'm just trying out different sizes. Seeing which ones are good, you know, trying out some things, figuring out some stuff before we there's also something on the back. It also says how bad do you want it on the back. I'll show you guys the shirt a little bit later as we get a little farther along. But yeah, thank you, I appreciate that. So this is an array, and so if we wanted to find the number 83 in our application, we could actually just, you know, we could actually refer to it as, you know, array. And then we can use brackets and say 2 because it's in the 2 spot, and that would return for us the number 83, and that's how we would know its location. Okay, so we've learned that about arrays already. That's great. So it would be super great if we knew exactly where the number 83 was already. Then we wouldn't have to search through the entire thing. We wouldn't have to iterate and, you know, look at the first box first, then look at the second box, then look at the third box. We wouldn't have to do that. That takes a lot of compute cycles, and again, it can take a long time as your arrays and things get bigger. So this is the problem that hash tables solve. They give us a table, they give us a way to know exactly where something is in an array, or exactly, or almost exactly, very close to exactly in an array. You know, always got to show off the guns just a little bit. This is Nike Dry Fit. You know, if you're going to be wearing Nike Dry Fit, you have to at least look like you tried to work out. I did not go to the gym this morning because, like I said, I hate Tuesdays. I said I hate Wednesdays and Thursdays, specifically due to deadlifts and squats. And I did deadlifts yesterday, and I was in fact crushed today. And I couldn't go. So I just went and did some work instead. But yeah. That's you know, tomorrow I will go do my squats as I'm supposed to, but you know, that's what the dry fit is for. It makes you look official even when you're not official. But cool. So how do we know where these things are? It's an array. You know, we know the spot that it's in, but how can we keep track of that? And hash tables are how we keep track of that. And the way that we actually keep track of this is with something called hash functions. All right, so hash functions are the way that we that we keep track of this. And so rather than just sticking something in the first slot and like, you know, okay, as we add things, we stick something in the first slot and then we just write that down and keep a log of it, that would take a long time, and that would actually present us the same problem. Even if we kept that log of things, we would still have to run through that log, and we'd have to still iterate through that log to find out where that thing was whenever we try to find it. So it would actually present to us the exact same problem, but hash functions allow for us to do something a little bit cooler. What are functions? Functions, you know, are little bits of code that can, you know, they're reusable pieces of code that that we can run by calling and that you can use over and over again. But the thing that they do is they take input, or they can take input. They can do some processing. So a little arrow here, do some processing, and then they can deliver some output, right? So what a hash function can do is we can create a function. We can create our own little algorithm to take some input. So let's say tonight we're going to be doing our hash tables with names. We're going to be using strings at least, but probably names. And so if we're keeping a table of names and we wanted to, you know, be able to search through this table to determine if names are there or anything like that, our hash function is going to allow us to basically pass in a name, pass it into our hash function, and whatever we write for our hash function is going to convert it. We can actually convert it to an integer, and an integer can pop out. So a number. Why would we want to do that? We would want to do that because that integer is going to be the index where it lies at. So we can write a function that takes a string, converts it into an integer, converts it to a number. We can choose how to do that however we want. That hash is our problem. It's something that we can do, and then we can simply use that to place it somewhere. So let's say we passed in the word hello, which is not a name, but let's say our function determined it did some stuff, and it determined that that was equal to 14. All right. And all that would mean is now we would stick the word hello inside of our array. So it would be something like this. Array at the 14th index would be equal to hello. So it'll give us that mapping. And why do we need that function? We need that function here because then we no longer need a table. So if we have a function, you know, if this is a pure function, it'll always give us, with the same input, it will always give us the same output. So we don't need to keep track of anything. We don't need to save, you know, the mapping between hello and the number 14 anywhere. All we need to do is when we need to know where hello is, we're saying, hey, we are looking for hello somewhere in this table. We're not sure if it's there. We can pass in hello back into our function that we write. It'll give us 14, and then we can just go check the 14th spot. And I'm gonna show you how something like that might work really quick. So function may be able to count appearance of strings. That's not how we would use. That's not generally how we would use it. But let's see. More so like this. And this is commonly how I did mine a little differently first, but this was a good way to kind of do it. Let's see if I can remember, or at least let's see if we can implement what I remember them doing here. And I'll make a. Let me go into a file really quick. I'll go array 0 index or 1. They are 0 indexed. Documents. Let's see. Then we want to go in documents, mastermind, streams, and decoded. All right, so we're gonna go into data structures, and this is gonna be a test file. This is gonna be us, so we can start to see some stuff happen. I'm going to make a file called, what are we doing right now? I already forgot. Hash tables. Yeah, there we go. My mind is always roasted at the end of the day. I'm gonna figure it out though. I'm gonna figure out how to make my day better so it's not roasted when we get to the end every time. Yeah, so we looked this up, that KCA. We did look it up, and there were languages that were, I think they were purely functional languages though. They were weird. I can't remember what they were. It was like Lisp, maybe. I don't know. There were some weird ones. But there weren't that many though. There definitely weren't. And a lot of them were really old. Like I think it's like COBOL. It's like 1 index, but yeah. So we are going to import, Just gonna import fumped so that we can print stuff out, so we can see some stuff really quick. But a hash a hash function might look like this, and this is how we're going to implement it later, so I'm going to give it to you right now. We're going to implement it similarly to this. But one, you probably don't know that, I don't know if we talked about it in Decoded 1, but computers work off of ones and zeros. We did talk about this for sure. And so even letters are actually referenced, or can be referenced via numbers, via integers. And so any letter can be converted to an integer, and so we can do that, and we can perform some mathematics. But again, this function is something that we have to create anyway. But let's see this. Let's get a func main in here, and let's actually get a func hash. So just like a hash function like this, which would take in, what do we need to take in? We said we're going to pass something into it, so let's try passing in a string. We'll just call it name, and it's going to be a string. And what are we going to output? We said that function can take in an integer and spit out an integer. I mean, take in a string, spit out an integer. Now your hash function doesn't have to be this. It doesn't have to be from a string to an integer or whatever, like anything like that. You do need to output an integer though for this, or like this is the paradigm in which it works best, is you spit out an integer, because that will give you the index location of this thing. So a function like this could look like this. We take in a name, and you can do this in a couple different ways. You know what I'm gonna do to make it very explicit? We'll do it very explicit now, and then we'll make it so that people can hopefully understand what's going on, and then we will simplify it and make it a lot shorter a little bit later, when we do it the second time, when we're actually implementing the hash table. So what you would want to do is, if you had a string, you kind of want to do a couple different things. You want to take each letter, each of those letters, and again, there's something called an Ascii table. So you could look that up if you wanted. There is, let me give you a link to one. But this is where you can actually see what a character, what integer a character is equal to. So we have something like a capital F is actually equal to, what is the number 70, I think. And so each of these, lowercase, uppercase, they all map to different things. And pretty much every language I know of has a way to do this somewhere inside of it. But what are you actually doing? You're breaking up the string first. So you have a string, you just split it up into individual characters. Okay. And so split string into, and again, I'm just taking it, I'm being very verbose here. You can do all of this. You can do this part in like 3 lines, like 3 or 4 lines, like the whole function, but I'm being very explicit so we can see what's going on before we do it. So split that up. How do we do that in Go? I don't even know why I thought to go down this route, because I don't even remember, but I'm gonna figure it out. I think you just do a strings package. Just, my rusty Go is it's coming back though. It's definitely coming back. And so you might do something like this. You might do split string. So if we want to split this up, let's say our split string is now equal to and I think you do a strings dot split, and I don't know what's first or last. Let's see. I think it has to do, I think we do the name first. So we're going to split up the name, and we're going to split it by nothing. We're going to split it by double quotes. Why double quotes? Because we want to split it by each letter. What is happening here? What is, oh, I'm in replace mode. Why am I in replace mode? Okay. That was weird. That was confusing me. All right, I think that's how you do it. And let's go here. And let's simply return split string really quick. And then down here in the main function, we'll simply run format dot println hash, and then we'll give it a word like hello or name or somebody's name or whatever. Well, let's do hello really quick. and let's see what this gives us. So this is kind of the first thing that's this is what's happening in a function like this. We're splitting up the string so that we have each of the individual letters. So let's see if that works first. Go run hash tables that go. New line on 16. Let's see, typos galore. We're starting off early. There we go. I'm missing a parenthesis, you know. Cannot split string type string as int in return argument. Oh, this is because I told you an integer would return, but I didn't convert it to an integer yet, so I need to say that I'm returning a string. This is a strongly typed language for you. So remember yesterday I said I was going to stop running over errors so fast. This error that we got here basically says, hey, you did a split string. You did a split string here, and you tried to. You ran the function, and it tried to return to me a list of. It tried to return to me a list of strings, but you told me I was going to get an integer back. That's what you wrote in your function. You said I should expect an integer. I did not get an integer. You caused some issues, so I went and changed that. And so this is actually an array or a slice of strings now. So each letter is broken up into its own little thing here. So we split it up. You don't need to split it up. A lot of languages you can iterate over this, but I'm just showing you how you might do this kind of raw, like we're trying to break it down to the base here. So we split up the letters. And now we might want to do something like this. Now that we split them up into an array, we can iterate over that. And so you can easily in Go, you can easily cast a string to an integer. You can simply cast it as type int and it will do this ASCII conversion for you, no problem. But we need to do this to each of the items. So there's a couple of different ways I could do this. I could convert this into, you know, I can convert it into a list of strings, and then I can actually convert the whole thing. But let's loop through. Let's try to loop through really quick. We'll do a for loop, and we'll say for letter in range of split string. So with this for letter and range is going to basically take the amount of things range is going to take for the amount of things that are in split string. It's going to iterate that many times, and I'm gonna say for each of those letters, all you're going to do is print out. We're going to print out the integer version of the letter. So we're going to iterate over that string, and then we're going to print out the integer version of it. We're going to cast it to an integer, and we're going to run that. So it should give us a printout of the numbers that each of these match. Can I convert letter type string into int? Hold on. I should be able to letter type string into. You should just be able to do that, shouldn't you? Like I can just do that. Can I not? We might have to go to the Go playground real quick. Can I convert letter type string into int? You should be able to just do it. No. What did I type in? Int. Now this should be. Let me go to Go playground real quick. What's up, everyone who just followed? How you doing, Clunky? Welcome to the channel. What's up, Dead Air? It's good to have you as well. Axis 10 love, welcome. Holding, love the name, welcome. Unjaded, thank you so much for the follow. It is good to have you all. So whenever because Go requires so much scaffolding, whenever you need, Go playground is a good place to go to whenever you just want to test something out really quick. But generally I can do I might have to do an int on does it need to be stated as no, it's already a string. Let me see something real quick. Let's just do the letter T. It might need to be a rune instead. Can I have our untyped string into, but what if it's a that'll do it. So I might need to convert it to a I don't remember this feels like I don't need to do this, but not a big deal. Let's see. How you doing, Foreign Live? Thank you so much for the tier 1 sub. This is just me being rusty, but fine. Let's see if we can double cast really quick. I don't think this will work. But I'm gonna try it out anyway. Okay, to type rune. Let me see here. T character. string. Say that again. Hold on. Actually, I might not need in range split string, or you need to use a loop, not split. I need to use a loop and not split. So I'm looping right here. I'm looping. Oh. Hold on. I think I need to use split string. Hold on. What is strings dot split? Golang. Let me see what this returns. Rune string var. Yeah, I could do rune string. So that'll convert the whole thing. I think. So you're saying, let's see, Goku, Drifto. Hold on. T character. I'm in T string, line 11. For range. 11. Rune. You're confusing me. Hold on. You need to use a loop, not a split, on line 11. 4-letter range. Oh, yes. Yeah. Yes. There we go. That confused me for a second. Well, so you're saying cast it here? Like this? But rune name, so if I'm doing range over this, I'm ranging over as the split is unused. I don't think if this is going to allow that to happen. Hold on, let's see this. 22 missing, comma, before new line on 12, 13. So actually not needed start. Hold on. Now everyone see now everyone's confusing me. Hold on. Let me think about this for a second. Let me think, let me look, and let me let me figure out where we currently are with this. Yeah, let's do this. So we split it up already, and this is not how I would do it anyway. Okay, I know what's happening. I know exactly what is happening. This is because I use the string dot split instead of, I was like this should work, because it'll work like this. Hold on. It will work if we did if we didn't, like, we don't need to split it. You're right, we don't need to split it, and we could just do it over we could just do it over name, and this, I think this would work. But I wanted to do it very explicitly, not RU, but over name, because it'll iterate right over everything. I think this will work instead. Imported, because I tried to do strings, dd, and int name. Undefined split string. All right, hold on. I'm confusing myself for a second. Let me step back really quick. let me step back really quick. So what we want to do is we don't need to split it at all. Actually, we can, because strings are iterable, you can iterate over a string. And this might be because, do I even need the, I'm not even sure I need the second return value, the error return value at all. And I'm not returning split string anymore. I don't actually need to turn anything. Let's just see if we can get it to print out the number value for some of this stuff. Oh yeah, you can. So yes, you can Control Z, but you still have to do EQ Explorer. You are correct, but the problem is you still have to save it. And then you have to Control Z it, and that is one extra key press, then Control Zing it. So it is one, it's one extra thing. Yep, letter. There we go. Hash hello used as value. What did that say? That's the only reason I usually don't do that, is because it's one extra thing in there. Let's see, 15 hash hello used as value. hash name, hello is passed in, function name's hash, func name, format.println line, hash hello. What are we doing wrong now? This is go. But the function doesn't need to return anything. The function doesn't need to return anything because we have a format.println in here. We don't need it to I didn't see it print anything. Right? It does if you try to print. Oh, yes. If you try to print main. No. It should. What? It's running in the hash. So it should kick off this hash function, and it should kick off this for loop, right? That's now I'm very confused. I'm very, very confused. I don't know if it's because it's late, but I don't understand. Why wouldn't it print? Why wouldn't it print? You're saying that does Google use this language eternally? Yes, they do. It was born out of there, but yeah. Just call hash. Okay, that makes sense. All right, so there we go. I'm not sure why my brain is broken a little bit, but that does actually print it. But this is actually not. This is printing the range number, and that's not what I wanted to print. Will this give me the actual, if I do range this way? There we go. This is what I wanted. So if I don't add in the modifier for the second return value, Go actually gives me the, it'll actually give me the index, but without it, it'll actually give me the number values here. So 104, 101, 108, 108, 111, and you can say, hey, I don't know if those numbers are correct. You could go check the Ascii table, which we could absolutely do, but you could also use a little bit of context clues here, and you can clearly see that 108, there's five things here, which is good. That's the same number of letters that's in hello, but also we've got two 108s right next to each other. We know that we have two letters together, and that, that can give us a good indication that this is happening. And so yeah, I was gonna try to be very verbose with that, but this is fine. This is how I'll write it anyway, to be honest. And so we don't need to split. Let's change this, and we'll just say iterate over string to and cast to integer. Okay, so great, we can do that. And so now we have an integer value here, but a hash function works a little bit more like this. So we want to take this, we want to take those numbers, we want to do something with them. Now arrays, what do we know about arrays? Arrays must be, arrays are a fixed size. We talked about that. We talked about, how underlying lists and things work, slices work, but they're using arrays underneath, but then they just do a lot of magic for you to extend arrays to be able to put them in memory properly. And so what we need to do actually is we need to do some type of function to give it an index number. But what does that mean? That means that the index number, whatever you write in your hash, whatever is calculated, must be one less than the length. It must be the length of that array. It can't be bigger than that array. So you can't just say, hey, go ahead and add all the numbers up for me. I can't say add, the value of each letter together for me, because it might be larger than the length of the array that currently exists. So that's something to keep in mind when you are creating whatever hash algorithm you want to use. But that is, again, up to us. The common way to do this is to, especially when you're just doing the examples and you're working with strings, is to add up all the letters. You add them all up, and then you divide them by however large the array is. So if the array is 100, is 100 spaces, has 100 items in it, you add them all up, you divide it by 100, and usually you do it with a modulo value instead, so that, to make sure that you'll get less. So modulo, we learned about that. That's in, one of the operators that you have for math. And so it divides, but it returns the remainder. And so if you're dividing by how big the array is, so if the array is 10 items long, if it can only hold 10 items, and you divide by 10, even if the number has a remainder of 9, it will it'll still fit in the array. That's the biggest number that you are going to be able to get. So 9 is gonna be the biggest number. That is the exact end of the array. It starts at 0, goes up to 9. So doing that helps. So how will we add these things up? The way that we add them up is let's set a counter up. So we're going to say sum of numbers. I'll say sum of letters, since that's what we're doing here. And we'll set it equal to 0 really quick. And then we need to add them up. All right, so right here, we're actually getting the number value. And so instead of printing them out, we don't need to print them out. We are gonna add them up. And we learned a couple of things in Decoded 1, and we learned some arithmetic operators. We learned how to add some things together. And so we can do that. So we can do sum is now equal to, and you can say sum plus int letter, but we can shorthand this. So what's happening here is this for loop is going to loop through all the letters in the name. So it's going to start with the H in hello, and it's going to get the number value for that, which was like 104. And then so it's going to take 104, and it's going to, sum is 0 right now, and so it's going to be 0 equals 0 plus 104, and it's going to assign that value back to what's on the left. So now sum's going to be 104. Then it's going to go to the E, and the E has another value, and so it's going to add that, and then it's going to go back over, and it's going to add that until it's all done. So we can shorthand this like this. I don't know if you all remember the plus equals, but we can shorthand it like this, and we can say sum plus equals int letter. So now it's just going to take that number value each time, and it's going to add it on to the sum. So now all we're going to do at the end is we are going to return the sum. Okay. And so we're going to return a sum. Actually, I didn't say 0, but we need to actually tell it to return an integer. And we will actually now print this. Print line. All right, so this now is going to tell us what all the numbers with the ASCII value of all the numbers in the word hello. We're going to find out what that adds up to. Undefined sum. It's called sum of letters. See, you got to make sure you specify things properly. Sum of letters and return sum of letters. Okay, now we are doing the right variables. And so these numbers added up equals 532. But here's what we can do. We can say up here, let's set a constant really quick. And we're going to say the value of the array. We're just going to set a constant really quick for the value of the array. Or so like size of array. Because this is just a placeholder for what we're going to be doing later. And let's say the array is, again, 10 items long. We can return this modulo size of array. So that's going to take that final value and it's going to divide it by 10, and it's going to return the remainder of that. So let's see what the number was. 532 was a number. That modulo 10, we should get 2 left over. And so that's going to fit in that 10 range. We'll run this. So the actual value is 2. And so we stuck into that function, we stuck in a string, and we did some calculations, and we returned an integer. And so now we could put the word hello in the second spot in that array. We could store it there if we wanted to. So that would mean, all that would mean is now next time if we have something that's searching for the word hello, we would pass that string back into the function, and it would say, hey, that equals 2, and then we could use that value to go directly to the second spot to get what we needed. And so you can also see that even if we change it to, well, I don't know, A, B, C, D, F, G, H, I, J, K, L, M, N, O, and let me go up, P, Q, R, S, T, U, V. I just want to add some numbers to this just to show you that it'll never be, like, it can't be more than 9. So 9 is the highest, and I need to do that because each the ASCII value for letters go up by 1. But if I go back to, if I raise it by one more, if I change it to W, this will make it a complete thing, and this will take it back all the way around to 0, and that'll be back to the first spot. So are you asking what is Big O Trapcoin, or are you asking what's the Big O of this? Because I can give you the link to the videos that we did, but Big O it talks about it's time complexity. It's talking about the way that an algorithm, the method and the time that it takes to solve a problem or run through a problem. So so what we're doing right now, this is not really, I guess this will be a linear, like this, I guess this will be an O of 1, because we're not really doing anything, but a hash table, so a normal traversing an array to match a thing is going to be a constant, time, but these hash maps, being able to set up a hash table is actually is an O of n. It's logarithmic, and so it actually increases it pretty greatly. I can draw a little picture for you of what the curve looks like for hash tables. I don't remember all of the Big O proper terminology, but I can show you what it looks like. I can show you what the graph looks like for that once we get there. So this is just what a hash algorithm might look like, and this hash algorithm is the key. This is the key to your hash table working, okay? Because remember, every time we pass in hello, we're gonna get the same output every single time, and that's how we can use that to know what to do. So that's what that's for. Any questions so far? What did I just hit about that? Anybody have any questions specifically about the hash function? Because the hash function is the thing that holds it all together. It's what makes this whole thing work. And maybe I'll rename this file really quick, so we can keep this to the side. Move hash table. And I'm so used to my other keyboard. It's really weird working on this laptop keyboard. Hash table to hash function dot go. All right, so that is the hash function, but you might say, all right, we can put all those things in, but isn't there a possibility that we put two things in there, two different words in there, two different strings in there, and those two strings, even though they're different strings, give us the same output? Absolutely. It is absolutely possible for that to happen. So let's go back over to here. And when you do that, so what happens? When the same input, or when actually not the same input, when different input gives the same output. All right, so right now we're just adding numbers up and moduloing. That means right now that any combination of letters will only return 9 values. 10 values. It'll only return us 0 through 9. So how is that possible? Like, how do we handle that? Because we know that in an array, once a spot is taken up, it's taken up. There's nothing you can do about it. You can only store one thing in that array spot. Okay, and that is true. Only one thing can exist in that memory address spot right there. But this is where we handle something called collisions. Collisions are when you again have the same output for the same for different inputs to your hash function. Plug two different things into our hash function, we get two separate outputs. That is problematic. How do you handle saving that? And the way you handle saving that is you have two different options here, and I'm going to draw them for you. The first option that you have here is something called open addressing. All right, so open addressing says this is 0, 1, 2, 3, 4, 5, 6, 7. All right, so this is it. Let's say we passed in hello right here, and our function said cool, hello is 2, so we're gonna stick hello in this spot right here. So this spot now is where hello exists at. Okay, now when something else comes along, and let's say, I don't know that goodbye will give us the same value. But let's say goodbye runs through our hash function and also returns a 2. Open addressing says, hey, I'm going to try to put you here. I'm going to check to see if it's empty. I know you're supposed to go here. I'm going to check to see if you're empty. If you are not empty, I'm going to move over 1. I'm going to say, cool, not empty. Let's move. You weren't good here. Nope. So we're going to move you over and put you here. And now goodbye is here. And it will continue to move over and over and over. Is this a good option? What problems can you foresee doing some open addressing? It can be pretty problematic. You can also run out of space as well. So this would only work if you had enough space for everything. So the things that you're trying to process, you got to make sure that array is big enough. But if that array is big enough, it gets really weird. And if you make sure it's large enough, it'll work. And so if we had something else that also matched this spot, and it would also try to match here, and then it would move over 1 and check and say nope, full, and it will move over again and it will fill in. So all of the things that equal a 2 will try to do the same thing and then move over and move over. Now it gets super weird, because now even when you have something that equals 3, you've got to now check and see if it's empty and move it over and over and over, and that is problematic. Again, works, but what it does do is it also causes you to lose all of the benefits, or many of the benefits that you get from the hash table. This then becomes very similar to simply traversing or iterating through this list. This is exactly the same thing that you would be doing if you were not using a hash table. Okay, it's the exact same thing. Shadow Johnny, great question. Why not just add it to the end of the array unless you want a specific memory address? You cannot add it. So adding, what do you mean by adding to the end of the array? It sounds like you're saying append it to the end of the array, but arrays, we talked about this last time, arrays are they're fixed. They're a fixed size, so there is an end of the array that you can't extend past. So you're probably thinking you're thinking about arrays and that you can just keep adding on to them. That's not true for an actual array. You cannot. It's a fixed size. You can't just add to the end. So yes, you could do these things, but we'll talk about why you can't with hash maps, or why I don't know if you can't, but there are reasons why you shouldn't. I don't think you would achieve any benefit. I think it would actually be very problematic for you to do that, and we'll talk about that. Eric.dev, thank you so much for the raid. It's good to have you here. Welcome. Everyone from Eric.dev. We are learning a little bit about hash tables this evening. So no Docker stuff today. Give you a little shout out here. That is not how you give a shout out. So welcome, thank you so much. So yes, make a template array. Yes, you could try to do this with a slice. We're using Go, so Go would probably give you, you could use a slice, but that would actually cause problems, and I'll show you why that'll cause problems when we get a little deeper. One problem is that when you're later looking for goodbye, you get hello, and you have to search for it over and over until you finally find it. Yes, so Vivasser is right. So you do lose, like I said, with this, with open addressing, you lose performance benefits. Bennies. You lose the performance benefits because now again you're just you're basically like if the thing is there, yeah, you got it fast, but if you have to keep checking over and over and over, it gets really weird. And then now everything actually ends up becoming out of order as well, so it is really it's super duper odd. It's super duper odd. One of the reasons why you cannot also, Shadow Johnny, why you cannot do this with a or at least I don't know of a way of, and I think it would be weird to do this with an expandable array, so like a list or a slice, is because that function that you have, that would mean you would have to change something in that function to into your hash function to make it allow for larger numbers. And now your function's not always given the same output for the same input. And so there wouldn't be a proper way to look up a location. And so that's why you couldn't do it as well. So this is open addressing. will cause problems. You know, you would lose the performance benefits. It would become more of a linear, a linear big O time for this. Yeah, and it works. It is not the way that generally you should do this thing. But so how should you do it? And the way that you should do it is something called separate chaining. And separate chaining is going to build on what we learned last week with linked lists. What's up, some coding guy? Thank you so much for the follows. Good to have you, Shadow Johnny. Lumberzak, I like that. That's pretty darn good. Axiom, welcome. Bully Ben, welcome. Foreign Live, thank you so much for the tier 1 sub. Good to have you all. Oh, absolutely, 100%. The DC baller, thank you so much for the prime sub. Thank you so much for the 2 months. Good to have you here. Thank you for the support. But now we're talking about separate training, and we're going to learn what that means. So open addressing works. Just move it over, keep checking, move it over when you need to. But we can combine the power of arrays and linked lists in a great way to do this. So this way, if we've got this right here, it's broken up, and you know the word hello, you know, ends up, and you know, we calculate it, we run it through our function, and it ends up that this is the place that it lands. And we run goodbye through the same function, and it ends up going to the same place it's supposed to go here. Instead of moving over to the left or the right, we can use a linked list in this space instead of doing anything weird. So we essentially can create a paradigm where we're essentially creating a structure where our array does in fact have a multiple values. It essentially has multiple values. And so if we store the head of a linked list in this location, then we can iterate through that linked list to find out what we need to do. So so let's say they're both in here. So instead of moving over, we would do something like this. Basically, goodbye would get added as a node. Remember, use the words that we learned before. It would get added as a node. And so I'll just put goodbye right here, or hello's right here. And it would have a pointer. And so this will be, let's say this is the head node. So I should have drawn it in the box, but not a big deal. And then when goodbye gets here, goodbye is actually going to get moved up. And so let's actually draw this a little bit different. So goodbye is actually, this little node here is actually the node that is goodbye, because it's the second one that's added. This is the new head of the linked list. Remember, linked lists are just individual elements with pointers to the next element in the list. And so goodbye would be here, and then goodbye would have a pointer to a new element, or not new element, but the old element that was hello. And you could continue to extend this chain. And so when you are searching for something in this hash table, you can quickly find, you get the benefit of quickly finding out where it is by, you know, passing in hello into our hash function. Hash function says, hey, great, it is in the second index of this array. And so you head to the second index and you say, cool, I see there are multiple things here. Now let me iterate through a much smaller data set to get to what I want to get to. So yes, you still are iterating through this list per se, but you're only iterating through a much tinier data set to find out what you need. So you get a big benefit from using them both. Get to the array, get to the exact location, and then you iterate through those things. Downside is the guaranteed traversal off the initial pointer. Yeah, yep. Guaranteed traversal, yes. So it is guaranteed. So these are actually called buckets, and this is how I want you to visualize it. I want you to visualize it like this. I'm going to draw a much bigger like array memory box or whatever. That's only going to have 3 in here. Those things, these things inside of the array, instead of the array holding a string or an integer, they're gonna hold what's called a bucket. It's called a bucket, and we know what buckets do. Buckets hold things. So I'm gonna draw a bucket here. Yeah, I'm an artist. In every slot is gonna have its own bucket. Yeah, and in buckets you put multiple things, so as you start to do things, you will start to stick as things match. You know, again, we'll put hello, we'll stick it in the bucket, and if we have to put goodbye in here too, we'll put it in the bucket. And then if we put hola, maybe that equals this one over here, so we'll put it in this bucket. And you just continue to put them on the bucket, and again, those buckets are simply linked lists. So exactly what we did last time, we'll just keep extending that linked list. Okay, we'll keep extending the linked list. So the initial run or search for something will tell us exactly which bucket it's in, and so we'll be able to you know, if we're looking for hello, it'll tell us, hey, go look for hello in the very first bucket. You don't have as many things to look through, you still got to look through the bucket, but it's in that first bucket. And imagine if there are 200,000 buckets. Knowing exactly which bucket it might be in will save you a ton of time. So yes, that is essentially how these work. So using what we learned last time with a linked list, and it's a linked list inside of an array, okay? And it really does reduce your search time. And so you should already be thinking, we're gonna be doing some searching algorithms, I think in 2 weeks or next week. I can't remember if searching or sorting is first. And this is something that you can use to manage that data. And so let's start to build this out. Let's start to build out our own iteration. We built out a linked list. I was going to do it from the linked list thing, but I didn't want to make it too confusing. So we're going to actually build it out slowly, but surely. I think we have just enough time, about an hour, to really go through and hopefully help us understand this. And we can see how this makes it super easy for us to do these things. And so again, it's going to be a little confusing, especially if, like, you know, you were still struggling with the concept of the linked list last time. Now we're piling something on top of it, but we'll try to go slow. We'll try to map out each piece and figure out what we're doing. Linked lists in the array address. Yeah. Yeah, they're pretty dope though. Better than your art. You know, sometimes I can draw okay, but most of the time I cannot draw okay. So, you know, it depends on the day, it depends on how I feel, if it's hot or cold. You know, you never know what it's gonna be. So like I said, I'm gonna try to run through and do this the best I can. Like I said, I just decided to pick every week. We're kind of just picking a new language. I mean, I went through earlier today and I was able to successfully complete one of my own implementations of these. I went back and looked at some other stuff, but we're gonna try to build it from scratch. I'll probably confuse myself 10 or 12 times, but it's okay. We are gonna get through it and it's gonna be fun. Help me out and we'll be all right. The goal is to understand how to do it, not necessarily to memorize how to do it in Go. It is gonna be different. Like I said, I know how to do it best in Python. That was the original way how I learned how to do it, and that's the way I kind of really understood it. It is actually super helpful, having learned it in another language so far. You know, it's pretty exciting. Makes it, you know, my mind works a little bit better now that I've seen it in another language. But here's what we're gonna do. We're gonna make our hash table .go, and let's get going. So what I did do though is I did take some notes on just the pieces that we need, and that's going to be super helpful for me, and I think it's going to make it super helpful for all of us so that we don't miss anything and have to go back and make it confusing. And so I'm hoping that just with this list of the things that we have to build out, we're going to put them in as comments really quick. We can just go through and fill in the pieces as we need them. All right. Yeah, I'm a big fan of the multi-language approach. It was super helpful for me when I got away from Python for the first time. Really helped me start to understand things, seeing things in another language. And that's why we do it here, because the concepts are a little more important. But we are going to start, just so you all are aware, we are going to start implementing. We're building some capacity now, but we're all going to start implementing single language courses to go along with some of these, so that people can actually focus on a single language. Some people are just trying to just learn JavaScript, completely understandable, which is actually going to be different from the web dev course. So there's going to be a specific web dev course as well. But yeah, we'll have a lot of different things, but we will do some language specific things, as we did at the beginning of the year with the introduction to coding with Python. We're going to switch that course up a little bit, and because that was really a decoded one course. and that's why we ended up moving it to Decoded 1. We're actually going to do a Python course instead. And you might be like, how is that going to be different? It's actually significantly different, because now you're focusing on the intricacies and all the weirdness with Python itself, rather than focusing on learning those things rather than the coding stuff. Are you implementing a hash table or just explaining Go data structure dictionaries that are hash table? No, we're actually implementing one from scratch. That is a great point. So Go has the ability for you, some of these things, you don't have to build yourself, but encoding things, interviews and stuff, that will ask you to do it. But like a map in Go can allow you to do that. Like Go has features for you to implement these things, but we're learning how to do it from scratch. But yeah, okay, here is how we're gonna do this. Like I said, all the notes I took were just the pieces here of the implementation, so I remembered how to do it, just because it's, first off, you learn this stuff. I haven't had to do a hash table. I learned how to do hash tables when I was like 21, and I'm now 30, and I'm a 30-year-old DevOps engineer, so I have not been writing code like this. So that's why this is here, and then we'll fight through it. You'll see me struggle. We'll struggle together, and we will finish it. What difference using the old hash function? A super good hash function. I like it. I like it. All right, so the pieces that we need, let me just get the import in here. This is the one thing that I hate about, not hate, it makes perfect sense, but I'm doing the Go package that I use for this, because there are other packages, there are the main things in here. It won't auto like fill out the skeleton template for me, because there's other things in here, so it thinks it's a part of the package that exists in here already, which is good, but not when I'm being lazy, is in the way that I'm being lazy right now. So we need to do a couple of different pieces, and a lot of different pieces. So first thing I have on here is that we need a hash table structure. So this should start to sound familiar from Tuesday. So what is this? The hash table structure is, we need to set up a hash table type, basically, and what that looks like. So start to think about what would be like, what is the hash table, what it is it actually, and let's put a description of it. Remember, our hash table is going to be an array, right? Remember, the hash table is just an array, but what is it of? An array has to be of a certain type. Remember, that's something that we also learned about arrays, is that, contrary to what people might think, when you're thinking about lists in Python and stuff, an actual array is of a single type. And so it's actually going to be an array of what? I'm gonna give you a quick second to kind of think about what it's going to be an array of. It's going to be an array of buckets. So we are doing the man, my mind just went blank again. We're doing the connected ones. We're doing the ones with the buckets. I always forget the name. Let me go back to my thing. What do we call these things? How do I go up a page? I don't know how to go up a page. I always forget what they're called. I never remember the names. That's why I wrote them down, but I did not write them down here. I remember them a second ago. One is called open addressing is the first one. So open addressing is the first one. We're not doing an open addressing implementation. We are doing a chain separation. Thank you so much. The bucketing approach. I like it. I'm just calling it the bucketing approach. But we are doing chain separation. And so we're using buckets. So this is going to be an array, but it's going to be an array of buckets. And it's going to specifically be an array of buckets of linked list nodes. So I just put this in here just to be clear when you're thinking about the structure of this data, what it's actually going to be. It's going to be a bucket. It's going to be an array of buckets that have nodes in it, and of buckets of nodes. Maybe I'll put that in there. But yeah, that's what it's going to be. So that's the first thing that we're going to need. And this is actually not in any particular order. I literally just rattled these things off after I did my own implementation. I just rattled off the pieces that I made in here. And I just made sure I had them all in here. So we're going to also need the bucket structure. So we're gonna need the structure for those buckets, and what in the world is, how do we know the structure for those buckets are? Remember, the structure of the buckets is just a linked list of nodes. So this is a linked list. And so we did this last week, so you should be able to reference the code from last week. I don't know if we pushed the code, but if we didn't, we'll do it today. But it is a linked list, so that's what this will be, a linked list of nodes. All right, great. And now these are actually, we actually need one more thing, which is the node structure. I'm looking at the things that I have here, and I'm ordering them now because they are out of order to how I think we should at least put them in the, like write them in this order. Maybe, let's see. The node structure of this is, so what's the node going to be? The node is just going to be, you know, a node of a linked list. And so we know what that looks like as well. And so this is just going to be where we are inserting, you know, the name and the next piece here. And then we need some methods. So I'll put this here. We're going to need some Hashable Methods. Just declare a bunch of random variables and you have an unlinked list. That is absolutely correct. 100%. You are absolutely right. So Hashable Methods. What are methods again? Remember, this is Go is not a class-based language. It doesn't have classes, but it does have these structs which can operate similarly to classes. And these table methods are going to be functions that act upon these structs, that act upon these types. And so we're going to need to add a few Hashtable methods. And what are those going to be? These are going to be functions that do certain things. Because of time, first, we're only going to try to implement an insert and a search. And another one that we're going to probably need is delete, but we're probably not going to get to the delete, so we're going to do it. I'll put it in here, and maybe we can add it in another time, or maybe we'll have time to do it. But I'm not sure, because we're going to talk about a lot of this stuff as we're running through it. And the other thing is going to be, so that's going to be the Hashtable methods we have. And man, this is more than I remember. Bucket methods. So we're going to need some methods that act upon the hash table. So let's think about this really quick. Why do we need these things? We need to be able to have the ability to put something in the hash table, right? Great. We need to be able to search the hash table. So if we want to find out if something exists in this hash table, we want to be able to search it, and we want to be able to remove something from this hash table. That's great. But because we are using this separated chain method, we're putting those things in a linked list. So not only when we actually go to insert something into our hash table, we are also inserting it into a linked list. So we need to be able to do that as well. We need to be able to put it in the bucket. The bucket is inside of the array. So if we want to put something inside of the array, we also have to put it inside the bucket. And so if we're going to do all those things here, we also have to add in an insert. Actually, just copy these. An insert, a search, and a delete for these things as well. All right, so bucket methods there. And then what else do I have? I have two more things here, which is hash function and initiate table. Okay, the order of this is going to be way different, but that's fine. We have the hash function here. So what is the hash function? That's already what we wrote. We already wrote this. This is going to be the thing that allows us to give some input and be able to get that integer output, so we know where to stick this thing. So we already actually have that code, and we can stick that here as well. And then the last thing we're going to need to do is initialize. We're going to need to initialize the hash table so that we can work with it. Why are we going to need to enable? Why are we going to need to do that? Why do we need a separate thing to do that? It's because we can specify an array, but now because it's going to be an array of buckets, after we create the array, we're going to have to fill it with buckets. And so we just got to make sure that that happens. And there's actually a way. Because I originally started implementing it in a different way. You can do it without doing this. But you're just gonna have some messy code in the middle of it, but it's fine. Well, this is I think, from what I was looking at, this is the best way to do it in Go. From what I can remember. Let's see if I can remember exactly what to do when we get there. So let's knock out the structures real fast. And the structures are gonna be pretty easy. Remember, these structs are basically you setting up types here. And so what are we gonna call our hash table? Let's just call it, so it's very clear. Let's just call it hash table. And struct, open it up, close it. All right, so it is an array of bucket nodes. That is what this thing is. So the variable that we're gonna put in here is, let's make this a little bit larger. The variable we can put in here, we can call it whatever we want. We can call it array. I'll call it collection, maybe. Now let's call it array. I don't know if array is a keyword I don't think array is a keyword in Go. I don't know. Okay, so this structure, when you're setting up a struct like this, you basically set a variable. So array is actually going to be a variable that's inside of Hashtable, but then you give it a type. So normally it would be something like integer, or it'd be something like that. It would be, integer or string. But what's the type that we're doing here? The type that we're doing here is an array. And so an array of, sometimes it'll be integers. We're going to be doing an array of strings, right? But this is not an array of strings. This is not how you define an array of strings. This is how you define a slice of strings. And a slice is not the same thing as an array, even though it uses arrays underneath. The way that you make it an array is to specify an exact number. And how you do that is to put it in here, and that now makes this an array in Go instead. I can't remember if I need to also specify. I think I also have to do this at the end, I believe. But yeah. But we could hard code this, but I think we should do how I did before, and I think we should just set up a constant so that you can just change it up at the top. And so again, we'll call this array size, and we'll set it equal to 10 right now, but we can change it later. And then so instead of specifying hard coding a number in here, and let's actually, instead of specifying a number in here, we can actually pass in the value here. And so we'll do array size. I'm a Go noob. That's completely fine. So it's funny because I'm not a Go noob, but I haven't written a lot of Go in the past 6 months or so. And I feel noobish for sure. I keep forgetting how to do very simple things, but it's we're all noobs. Definitely all noobs. So this is basically, I'm setting up an array. So hash.array is of type array. It is an array of whatever size that's here. Actually, that's not the whole thing. Array size, and it's an array of strings. It's an array of strings right now. This will equal 10. So this is the same thing as, delete inside brackets. Same thing as this. Exact same thing. Okay. Exactly what it is. So we'll just put that back. All right, so now that's our whole structure. And so I did put array of bucket nodes. Some coding guy, thank you so much for the tier 1 sub. I approve of what's going on here. I appreciate that. I really do. Thank you so much for the support. Phenomenal. What's up, Last Miles? How you doing today? Hey, Anna Codes, how are you doing? Let me give you let me see. Let me move my mouse. This 2 computer thing, I'm gonna get it one day. Let me give you a shout out as well. Because Anna does in fact code. But yeah, pretty dope. How's everyone doing tonight? So we have the structure of our hash table. This is the whole structure. How's it the whole structure? The whole structure that it needs to be is an array, and it needs to be an array of buckets. Okay. And so this is the type of buckets. But is it the type of buckets? We said we're gonna make an array of strings, but that's not actually what the array is holding. The array is actually holding buckets, so it's actually not string. It's actually not string. I just put that there because we're used to seeing a type that's like this, and I want you to get it in your mind that this is a type. Let's set up the bucket first, and remember these structs are actual types. They're types in here, and we're gonna need to make that the type instead. So here we go. We will do we'll set up the bucket, and then we will change that above. So what's the bucket structure look like? A bucket looks like this. I'm just gonna actually call it bucket and call it a struct. What does a bucket look like? A bucket needs a couple different things, and not really. It's just a linked list. Remember, it's a linked list of nodes. What did we need last time to make a linked list? All you need is a head node. All the linked list really needs, all that's essential, is to know what the first item in that list is. That's all. Whoa, that was gross. Little either mustache hair or a little bit of chin hair somehow got into my mouth. I didn't like that at all. Very uncomfortable for me for a second or so. But yes, so all we need to do is we need to simply reference this head node. And so the way that we're gonna do that is it's gonna be of type node. And remember, we don't have to set up a node yet, but that's all it's gonna need. And we probably should do this in reverse order. Why would we do this in reverse order? Because it make a little more sense. So a node is gonna look like this. So a node is the smallest element. Why is a node the smallest element? Remember, it's each item in the list, and a list is gonna be inside the bucket, and the bucket is gonna be inside the array. So maybe we should have worked upwards. And so we do type node is a struct, and remember, you call this whatever you want, but we're gonna call it a node to make it easy. And what does a node need? A node, I'm gonna put name because we're gonna be passing in strings of names, and the name is gonna be of what? It's gonna be a string. And what else does an element of a linked list need? It needs the value, and it also needs a pointer to the next item in the list. And so the next thing it's gonna need is a next, and it's going to be a pointer to a node here. All right, so let's move up. Let's go back up and fix these things. So a node is just going to have a string and a pointer to the next item in the list. And then a bucket holds a node. And so it's a linked list. So all it needs to know is the very first. It needs to just know the head node. It needs to know the very first node. That's all it needs to start to traverse the linked list. And then the hash table needs to have an array that holds buckets. So not a string. It needs to hold, excuse me, boy, that was gross. But it needs to hold buckets, a bucket. All right, so we have an array of buckets, which right now is going to be of length 10. We have a bucket, which is a linked list, and we have a node, which is the nodes for that linked list bucket. It can be pretty confusing. I know it's a lot of things, but that's where we're at. Let's see. So node has value. Yeah, I mean, node does have value. Name is value. We can change the value. I think value makes sense because value will allow us to add in things that are not names. Well, we can do that regardless, but I think value is a little cleaner. So I think that's good. Cool. Or we call it key or whatever. Naming things is hard. But yeah, I think that's all the structure that we need. That feels right. That feels like all we need right there. So these are the different types that we're gonna need to get this done, I think. So like I said, don't let me, if you all see me start to do any of the deletes, don't let me do the deletes. We should really get the inserts and searches done before time doesn't really run out, but before it gets too late. And we'll do deletes last if we do have time. So if I start doing deletes, say, hey, stop doing deletes right now and finish out all the rest of the stuff. So this is a little bit harder. This is gonna be a little bit harder to do in order. This part is gonna, we're gonna be flopping around a little bit just because of the way the data moves. So yeah. Let's see, what is the easiest way to get files from local to remote server and vice versa? Easiest way is, for me at least, is SCP. It's secure copy. It's through SSH. It's basically the same command as SSH. That's the way I like to do it. From local to remote SSH. You could curl it as well if your address, or if you have a web address that you can grab it from if you want, but SCP is what I would use. You don't need any special, a lot of people like FTP, which is file transfer protocol, but then you need to have a FTP server and you need to have an FTP client, and usually the FTP server is not there by default, so SCP is generally the fastest way. Netcat for big win. Yeah, go for it. I'm not, I like to keep my life simple, and that's all that matters. Keep it simple. Keep it simple, smarty. We don't do keep it simple stupid over here because we are all the smartest. We keep it simple because we are so intelligent over here. Let's see. All right, so we're gonna need some hash table methods, and when you think about it, these hash table methods are also gonna need bucket methods. Okay, why are they gonna need bucket methods? They're gonna need to utilize bucket methods inside of them. And why is that? Remember, if you stick anything in the array, that means it has to go in the bucket because every array is held by bucket. But let's actually do that first. Let's actually do that first. Let's actually, you know what? No, let's start ourselves with our main function so we can start seeing stuff happen really quick. And let's try something out really quick. If I don't do a full initialization, let's see what happens here. Main. Let me see what we get, and let's start building. I like this actually. Let's do it this way. So let's do our what are we making? Table. Man, our table is equal to ampersands. What do we call this? Hash table. No. I don't know what happened. I don't know how my cursor got up there, but hash table. So we're gonna make an empty hash table here, and we're gonna format.println it. Print line, and we're gonna print out our table. Okay. So all we did was set up some structures. We just set up some structs, and then we are going to try to print that out. And so I will let me see if I can get my Control W. Yeah, that's one more key press. It is one more key press. It's one more key press, but it's fine. It does work. It works just the same. And if I do go run hashtable.go on line 9 and 10 unexpected new line. Let's take a look at that. FG. What did I do here? Is I'm not supposed to have, maybe I'm not supposed to have these. I can never remember when I'm initializing the array. Oh, no, I don't need that because it's already the, okay, got it. It's already the struct there. So I don't need that. Okay, here we go. Oh yes, SCP with a, as in cow, or as in cat, or as in cactus. You know, you got to pick the right words so people can understand, you know, SCP. So check that out. Take a look at all of those nils and count them up. How many nils do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decakill. See, I should have been the guy on Halo that said double kill, triple kill, quadruple kill, quintuple kill. Okay, I should have been that guy, but I wasn't that guy. So if you know a game, put me on it, because I want to say some stuff like that, and it'll be fun. It'll be really fun. I always wanted to do some voiceovers and have a, you know, just everyone doing my EA Sports is in the game guy, you know. That's I need that. Yeah, monster kill. I want to be that guy. So if you know a game, if you work at a game company and you want me to be the voice, I want to be the voice. I'm telling everybody that right now. What's up, Last Miles? Thank you so much. Thank you so much, Last Miles, for the follow. It's good to have you here. All right, so there are 10 items here. This did in fact create us an array that has a bunch of empty values, a bunch of nil values. So great, you know, nice. You might, so we have that piece. The structure is fine, looks good. It is actually creating that thing very nice. But what we have to do is, because we want buckets inside of there, we need to now initialize this thing with you know, with these buckets. We need to push these buckets into there. So what is our hash function going to look like? We basically need to, not our hash function, our initialization function is, this is not a method or anything. We can just do func initialize. I'm going to put init table. How about that? Init table. So initialize table. It's not going to take in anything because we don't need to pass in anything to initialize a table. But what we do need to do is we do need to output something. What do we need to output? We need to output our table. And what is the type that we are outputting? And I think the type that we are outputting is, do I need the pointer value here? I think I need the pointer value here, and we are outputting a hash table. So we're not putting anything in, but we are gonna return a hash table. What's up, T13R? It's good to have you. Welcome to the we need a name for the, you know, the danger zone. I don't know what the stream is called, but you know, welcome to Mastermind Academy. It's good to have you here. Sally needs to wander away. Deal. All good. Embedded board thing. Do what you got to do. I'm glad you came through. I was lurking a little bit earlier today, but it's good to see you here. I appreciate it. Very slowly working on a chessboard game. A just BR game. That's a good one. Doesn't have any plans for sounds yet, but yours could be first later. That's pretty cool. That's definitely see, there we go, Mr. Pinnacle. You got it. Checkmate. I like it. We got it. I want to be a part of everyone's chess game. I love it. We got to do it. All right, but let's get going here. I'm tripping. Let me move this out of the way. I moved too much stuff in the way. Okay, so what do we need to do when we initiate this table? We don't take anything, but we do need to initiate this table. So we can kind of take the line that we did here. We can take the same line, and we can get ourselves, a table right here. Okay, so that initializes it. That's great. But then what we need to do is we need to iterate through this array, and we need to basically push a value into there. And so I'm gonna say for I in range, let's see if this works. For I in the range of hash table, so this is just gonna start to iterate through all of the things that are there. I think this will work. I think I can do it like this. I think I can do hash table dot. Oh no, actually we need to do this. Hash table dot array. So why do we need to do hash table dot array? Hash table is a structure that has, that array inside of it. And so what we need to do is we need to iterate over that array and not over the hash table itself. The hash table array is the hash table that we care about. And we're gonna set whatever's in the I spot equal to basically a bucket. And I think we can just do, ampersand bucket. Delete ampersand bucket. Is that what we called it? I think we called it bucket. Yeah, ampersand bucket. And I think this is how we can do it. And it should run through, and it should set all those values now to a bucket. So all those no values should now end up being buckets. And again, so what's happening there really quick? What's happening here is we're creating kind of a little, we're creating the hash table using that struct that we have up there, and then we're iterating through the array that exists within that thing that we created, that array that had all the nils, and we're setting each index value to a bucket, a bucket type. We're sticking a bucket in there. So array with the I, this I is going to go, it's going to iterate. So it's going to be 0 the first time, then 1 the second time, then 2. And remember, that's why that index is so important. That index is going to be able to allow us to specify that quickly. And let's actually do, let's return our table. Okay. So that's going to be that. And then if we actually do, let's remove this line and let's actually print out, let's actually change that to our table is equal to, and let's call this init table, and we'll just call init table, and that's going to, put it into the value our table, and then we'll print that value out. So before, remember, okay, so we got an error. I made a mistake. On line 36, there's a colon there. Declaration 4. Did I do something wrong on 36 and 38? Of course I did, because that is what I do best, is something wrong the first time we try it. Init table. Oh, this is supposed to be a star because we are referencing that and not an ampersands. I think that should be the only problem. Okay, undefined array hash table array. What was that error? Okay, it says hash table array undefined type hash table has no method array. Okay, that seems a little odd. Hash table. Oh, that's because we need to do yeah, it's not hash table, it is our table. This is not a thing. It's our table array. There we go. And not hash table, but our table. Why is it our table? Because that's the variable we're using for the initialized hash table here. Never seen Go language before. Does it have automatic garbage collection? It does. Okay, so now this should work, I think. All right, so now you might say, ooh, did that work? I can't really tell, but what you're seeing right here is 8 or 10 memory addresses. These are your memory addresses here. And so it does work. It does in fact work. And these are now the pointers to those buckets. This is the pointer to those buckets. And so we now have an initialized table to work with. And so now we have an entire array that has each of the items in the array that already contain a bucket. All right, so we have that part now. And then now we can just go through and start to do the functionality. So first, let's implement that same function, that same hash function that we did before. So we're gonna take in a string. This is gonna be the part, this is the key to the whole thing. We're gonna take in a string. We're gonna iterate over that string. We're gonna convert each letter to an ASCII value. We're gonna add those up. We're gonna add up the total value of those things. And then we're gonna divide it by the amount of things that is in the array. And then we're gonna run modulo on that actually to get the remainder. And so that's gonna give us our output. So let's set that up really quick before we do any of our methods. And so we'll do hash func hash. This func hash, does it need anything? Yes, it does need something. It needs a string. It takes a string. Let's call it value. And is it going to output anything? Yes, it is going to output something. It's going to output integer. Remember, we just did this. I almost forgot that fast. The way that we did this is we simply iterated over this with a for loop. And we just said for letter in range of the value. So it's going to go through that value string, and what it's going to do is we need to convert it using int, but what we also need to do is set up a counter really quick. So let's do the same thing that we did before and set up a let's see, set up a sum. Let's set up a total. How about that? Total. Our total is going to be 0 up here. And what we're going to do is we are going to do total plus equals int letter. So it's going to, using that for loop, it's going to iterate over each letter. So it's going to get to, if we pass in hello, it's going to go H. It's going to convert H to an integer. So it's gonna give us the ASCII value, and then it's gonna add that, whatever that value is. If it's 10, it's gonna add 10 to the total, and it's gonna start the loop over, and it's gonna go to the O, or to the E, and do the same thing, and it's just gonna add this up, and this number is gonna keep incrementing until we have a big number. And then what we're gonna do here is we're simply going to return, we're simply going to return our total. We're gonna return our total modulo the amount of things. That's why we set up this constant up here, so we can use it in multiple places. So we're gonna divide it by the array size. We'll do that. So it's gonna take the total, it's gonna divide it by the array size and return the remainder. That's what modulo does. All right, so that's our hash function. And again, our hash function can be whatever we want our hash function to be. This is just a common paradigm for a simple hash function when you're first learning how to do these hash tables. All right, and so how can we test this? How can we make sure this works? The way is we can take our table. We can take our table and we can pass in a hash value. I wouldn't even need to take our table. We can just pass in a hash value. So we can just do format that print line hash. And let's try to do first, let's do something simple that we can look up. Let's do A and let's do B. Let's do A and B. A and B together. We can look up that on the ASCII table. Let's look that up really quick, and we can determine what it's going to be before we do it. Lowercase a and lowercase b. So 97 and 98. I don't like to do math. Oh, well, 97, 98. That's 200 minus 3 minus 2 is minus 5. It's 195. And so to confirm that, let's do what? 97 plus 98 because, you know, we got to confirm it. 195. I might be the smartest person you've ever met in your life. I can do simple addition in my head or complex addition in my head, and you should be impressed. I hope everyone is impressed. So 195 divided by 10 is what it is. You know, it goes in 19 times for 190. That leaves over 5. So we should get a remainder of 5 when we pass this into the hash table. So we should get that. Let's see if we do actually get it. I have some errors first on line 58 and 59, missing comma before new line argument. Let's see. Your boy makes all kinds of errors. 58. Print line our table. Oh, I need to close this. Close it. You're impressed? Yes. Quick maths. Yep. Quick maths. I'm glad you're impressed, as you should be. But check that out. We did in fact receive 5 back. I know I should have probably removed this, but we did receive 5 back. You know, if we want to do it again, we can remove. Let's do BB. And so BB will increase the number by 1. So now our remainder should actually be 6 instead of 5. And we do get a remainder of 6. So our hash function is working. We'll never get back a remainder larger than whatever we are moduloing by, which is 10. So that is great. So we've implemented that function. So what do we have so far? We have the structure for the hash table itself that holds an array of buckets, and in those buckets are actually linked lists. We have that set up. We also have a way to initialize our initial one. So we set up the structure for it. We have a way to initialize our hash table that's set up properly with the buckets, and we have a way to hash things when we're ready. We have a way to actually figure out where to place them in the array. We can pass in the string, and it'll do some calculations, and it'll give us an integer to place it where we want to place it. What's up, Atmospheric? It's good to have you. Thank you so much, Mr. Pentakills, for the Twitch Prime sub. But thank you so much for the follow, Atmospheric, as well. All right, so we have that much done. Now let's do the fun stuff. Let's do some sweet inserts. Yeah, let's get the inserts out of the way here, and we're gonna be doing them kind of in tandem because it gets a little bit messy here, to be 100% honest with you. It gets a little bit messy here. So how do we get something into this table? Like, I really want you to take a little bit of time and say, how do I get something? If I want to insert something into this hash table, how do I get it into the hash table? The way that I get it into the hash table is I take the string, I hash it, I get an integer. Once I get the integer, I know exactly where to, I use that integer as the index, so I know exactly where to put it. Okay, I know exactly where to put it inside of this thing, and so that would work pretty simply. So first, let's set up this method signature really quick, so that we can start that. But I want you right now should be just thinking through how you might get something in here, because there are a lot of steps to this, or there can be a lot of steps. So our first function is going to be this is going to be a method on the table itself. So this is going to be the receiver here, and we're going to call this let's just call it insert. Let's call it insert table, so we can differentiate from the insert on the bucket itself. And insert table, what's it going to take? It needs to take a value, so it needs to take a string. And it's going to it doesn't need to output anything. I don't think it needs to output anything, but if it does, we will fix it eventually. And so just to make things easier, I'm going to take this and I'm going to yank it, because search and delete are going to be very similar to this. And so we'll just set these things up as is right now. So we'll change it from insert right here, we'll change it to search. And actually, remember I told you we're not going to delete right now, so I will remove this for now, so we can save a little bit of time as we kind of move through. All right, so all we're going to do here is we are simply going to first we need to pass through we need to figure out what the index is going to be. So we need to, we have a string is going to get passed in to this method. So, you know, whatever the value of the string is going to get passed into here. We need to take that value and we need to get the index that we need here. So we can call it whatever we want. We can say index to get it. And all we do to get that is we're going to run the hash function on whatever's passed in. So the string that's passed in is called value. So we are going to hash that value, okay? And then normally the thing that would happen is, you know, we would simply say, cool, now that we have this value, all we would have to do is do something like this is, you know, whatever that hash table is called. So our table, at the index value that we calculated is going to be equal to value. It's going to be equal to that string. This is all we would have to do in a normal scenario. Okay. If we were doing the other method, which is the open addressing, if we were doing open addressing, it would look something like this to start. There would be a lot more conflict handling around this, but essentially it would be this. But it's not this. And why is it not this? It's because we're sticking this into a bucket. We are not sticking this. We are not inserting this directly into the array. We are inserting it into the bucket that is in the array, in the array slot. And that bucket is what? A linked list. So we have to get this in to a linked list. And so the way that we do this, the best way to do this is for us to actually have another method for the bucket itself. Like we could handle this here, but we shouldn't handle this here. We should handle that elsewhere. But so basically we would return, all we're gonna return here is the table dot array. So we're actually, so we do need to return because we're gonna need the actually, are we gonna need a return? If we're inserting, I guess if we want to just get this thing back, I guess we could, I don't know if we need to return it though. I guess we can save the value. Let's see. I'm just gonna put table.array. We'll save this. We'll either return this or save this to value. I gotta think real quick. I don't really remember what I'm supposed to be doing here. For the insert, and we are going to call, all we're going to do basically here is we are going to call table.array so table.array dot whatever the thing is going to be, is we're going to call a new method called insert down here. So it doesn't need to be called insert, but we're going to need another method that exists again on the bucket and not on the hash table itself. Okay, that's the part that gets a little bit weird, and it'll actually be array. We'll have to call it on the bucket. So that's where the index is going to come in. And so table.array is going to reference the whole array. If we include the index, it's going to choose one specific spot, which is now going to be a bucket. And then again, we can put in you know, maybe like an insert to bucket. Maybe we will run something like this where we're going to insert it into the actual bucket, and then we're going to insert whatever the value is into that bucket. So that's all our, like when we're inserting something to the table, this is all we're really doing. We are, you know, inserting it in, learning how to insert it into that bucket, and we need to allow the bucket to, you know, do what it needs to do as well. So this is where things get a little complicated. So this is where the insert, this is where all the magic happens for the insert, is actually in the bucket rather than anywhere else. And this is where we're gonna have to do a little bit of magic here. I'm trying to think if we want to, if we can do this in a couple different ways. We can use the search function, like if we already know how to find things, we can actually use the search function here. But let's just figure out how to properly insert this thing. So this is gonna act very similarly to, let's save this really quick. This is gonna act very similarly to what we did here with the linked list. And so I'll open this up side by side a little bit. But for linked lists, when we wanted to add a node to the list, it's going to act very similarly to this, where we, set up a next element item and set it to the head. We set the next element as the head. And then we basically, just are moving some of these things around, but we're not going to be dealing with length this time on here. We shouldn't be dealing with length. I don't think we need it for anything, but maybe we will get to it in a second. But like our first iteration of this can look like this. All right. Wait, why is it? Oh, I haven't started writing anything yet. So same thing, let's start our method signature really quick. We need to have, we're gonna do this on the bucket. So before, when we're doing a table, let's actually call this bucket here. Actually, we're already using bucket for a name. That's gonna make it a little bit confusing. Let's call this, let's call it array, let's call it node bucket. Sure. And this is going to be of type bucket. And we'll call this insert. What do we call it up top? Insert to bucket. Insert to bucket. So we'll call it insert to bucket. And if we're going to insert the bucket, what do we need? We need the value to insert to. And that value is going to be, what's up Linux, Linuxy 1001, welcome to the channel, thank you so much for the follow. But the value, which is a string, I don't think we need a return value here either, but what we do need to do is move the little bit of things around here. So we need to set up the new node. We need to set up the new head of the list, because remember, every time you get a new item in the list, we need to move the first thing to the second spot. Whatever's in the head right now needs to move to the second spot, and then we need to make the current thing in the head that has a pointer out to the other node. So the way we had it set up in the other thing, we did something like this, like next node is now whatever the ampersand bucket. So whatever's in that bucket, we need the node of the current head. I think we need something like this, or dot head. I think is what we need. Because what's bucket? Yeah, bucket dot head. I think is what we need here. And what else? Wait, stop scrolling. Next node equals the current bucket dot head. Okay, so we're basically saving the current bucket dot head for the next node. And then I think we need to do this value is a new node. So we need to kind of create this as a new node, and we need to do a next onto it basically. And so we need to do hold on, let me look at this again. My mind's blanking a little bit. I'm gonna confuse myself again. Where's add? N dot next element. How do we do next element here? The next element needs to be head. So not what we just did, not next node. It needs to be the, oh, this actually needs to be, so bucket dot node bucket, node bucket dot head dot next. That seems a little bit weird. I think I'm confusing myself a little bit. What we need to do is, right now is we need to take, sorry. Let me talk about what we need to do and work through it mentally really quick. We need to insert this into a bucket. So we're going to call this method, we're going to be passing in the string. And so we're going to be calling this on, we're actually going to be calling it on a bucket. A bucket is just going to have the node. So we already have the node. We already have the node bucket.head should be there and available for us. No problem. And I think this is actually node bucket. So we have that. So we have that available to us. But what we need to do with it is we need to check. We need to move the current item to head.next. And then we also need to update the value to whatever this new value is. Okay. All right. Let me think about that for a second. My mind is kind of blanking out a little bit here. Let me take a little sip of water. Where'd my water go? Did I drop it? I did. Got it. All right. Let me also draw this out because it's confusing me right now. So we'll go over to our whiteboard real quick. And what we need to do now is, I'm just looking at the code here. We need to take, we're doing insert into the array. The array says, the insert into array says great. Take the string, and this says excellent. I have this string. I'm going to I'm going to hash your string, which is going to give me an index. Great. We have our index now. Extra phenomenal. Thank you, Yago. Welcome to the channel. Thank you so much for the follow. After we have the index, we're going to basically say, all right, cool. For our, we're going to take that index. We're going to stick it into the actual index of the actual array. Yeah, the array index. And then right now we're going to try to insert something into this, but this thing is a linked list. All right. So now we're writing the method for the linked list to say, cool. All right. If we want to insert this string into this insert method is going to pass along the string. And so now we're going to try to insert the string into the bucket. And what that means is this is a linked list. So we need to make the string, we need to make the current head. We need to set it to, the head.next. We need to set it to the pointer. We need to save that at least, so that we can set it to the pointer. We need to make the current item. Oh, so maybe we're not passing through. Are we going to be passing through a string, or is this because we need to pass in? We might actually not be able to do an insert until we can search. Or it might make it harder for us to do an insert until we can search. Okay, that might be my problem. That might be my mental problem here. Let's try this out. Like I said, it would get real weird in the middle with the ordering of things. This is what I ran into the first time, but I'm trying to remember how I resolved this. But it's okay. We got it. The way we'll do it with search is we'll do it the same way that we did up here. Let's see if we can get this right, and maybe it'll give me some insight on what we need to do. But for searching this thing, so what is searching going to do? And this is going to move back upwards as well. We're going to need to be able to search after we discover an index for the node, which is pretty easy for us to find. We're going to need to search through the thing that we are using. And so what we're going to do here is we are simply going to go, we're going to grab our bucket. So we're going to say, no bucket again, which is in fact a bucket. So same signature as we have up top. And we're going to say search bucket. And the thing that we're going to take in on the search bucket is the exact same thing. So we're going to take the value of the string. All right, and let's see if we can do this. So we have this here. And so to search through this, we need to know what the head is. We need to get, because it's a linked list, we need to get the node that's the head. That's all we need. That's the only thing that exists inside of the linked list. So all we're gonna do is, let's just set up something for like our current node or lead node or head node or whatever. And what are we gonna set that to? We're gonna set that to node bucket dot head, because remember, a node bucket is just a linked list that has this thing here. Oh, cool. I mean, I'm glad it is, because I'm trying to think through it, because I literally I was telling everyone I have done linked lists previously, like in Python and stuff, like years ago when I learned. And so I put this together. I put the curriculum together, and I was like, oh, cool. Like, I'll figure out what language we're going to do it in by the time we get there. And I was talking to someone earlier today, and I was like, I've never implemented a hash table with Go before. I'd never done it. I actually, I've never done it since I learned Go. And so I spent like an hour and a half earlier today implementing one, and it was a little sloppy, definitely a little sloppy. And then I compared it to some other implementations, and I learned some things, but it worked. And so I'm trying to remember some of the stuff that happened here, just trying to follow, but all good. I think we're on track. I think we'll finish no problem. But what we need to do is we need to get the current node, the current head, because as long as you know the head, you can then traverse through everything that you need here. So the way that we're going to do this is we are going to go, we're going to loop through this the same way that we looped through in the linked list before. So remember, we used a for loop, but we are going to do this a little bit different. So let's say this thing doesn't exist. Because there might not be anything in that bucket. That bucket may be empty. So we do have to actually check for that. So we can check for that. We can do this in a couple different ways. I can say, if it equals nil, we already saw what that empty thing looked like. And so we can say, if it equals nil, do something, or we can actually check for a value, whatever you'd like to do. You just have to adjust the rest of your logic accordingly. But I think we can do it this way. And this is going to be good. So this is the search functionality. This is not the insert functionality. The search functionality is, again, going to allow us basically to say, hey, does something exist in this thing? And so actually to put something else here, because we're gonna say, does something exist? And if it does exist, we're gonna have to return a value, which is gonna be a Boolean value. So we're gonna have to return true or false to say this thing exists or does not exist. And so that's what we're checking for now. So if I check for Aaron in here, I'm looking through, we check if the current node is nil, because if it is nil, then we can just kind of get out of here. But we need to do some more logic, and I don't want to have to do two unnecessary comparison statements. And we can basically say, hey, if it is not nil, that means there is something in there. We can say if the current node equals the thing that we passed in. So value, it's going to check it against value. Value is what we're looking for. Value is what is passed into this method. So if Aaron gets passed in, it's going to say, all right, I'm going to find the head node. Cool, I got the head node now. I'm going to take that head node. If it is empty, if there's no head node, that means, I didn't match anything. Then I'll do something else. But but this for loop is going to allow us to iterate multiple times over this. And it's going to say, hey, if there's something there, great, keep going in this loop. And go ahead and run this loop. And then the first thing we're gonna do is compare current node to the value that was passed in. All right, great. If that value is passed in, we can simply return true. We can say, great, this thing is in fact here, and you're good to go. Pretty simple, right? Not a big deal. I found you, great. But if it's not, it's false. So we could do an else return false, but you don't really need to do that. You don't need to, that's not a common paradigm. When you're first learning, it is, but we don't have to do that. But we actually have to do something else before we do that. Even if we did it else return false, we would have to do something else in the if, and we would basically have to set the current node to the current node. Actually, I don't even think we need to do, if we're searching, oh, this is if it's not current node dot next. All right, so why do we need to do this? We need to set the current node to current node dot next because this needs to, this actually is going to need to iterate through this over and over again. And you'll see how we'll do this. We're going to actually do, oh, I'm tripping. I'm sorry. Thank you. Very, very sorry. Very, very sorry. I do that a lot. That's why I need to use the whiteboard more, but my bad. But that's what we're doing here. We are simply going through this. We're setting the current node, the current head node. We are checking if that current head node is empty. If it is not empty, so if there's something in there, then we're gonna go ahead and evaluate that. We're gonna say, hey, check the first option, see if it matches the thing that we passed in. If it is not, I mean, if it is, then we'll go ahead and return true. Else, set the current node. So change this up here, change the current node to current node.next. So this is going to traverse this linked list. So it's going to go to the next thing. And because it's still in the for loop, it'll just go back up to right here and it will go to the next thing. It'll compare it. It'll go through, it'll compare it. It'll go through, it'll compare it. It'll go through. Cool. So you can say, all right, well then how do I handle the, once it gets through everything to actually return false, and you just return false down here. So if it is true, it'll hit this return true block first, and that will, end the loop because it will exit out of this function. But if not, it will, in fact, it'll get through all the nodes. And when current node.next is nil, basically, it's not going to run this piece. So, when it goes to current node.next, and that'll be the only node that has no pointer value is going to be the very last node that's in there, which is ultimately the first node that was entered. And so it won't run this for loop at all, and it'll drop down to this return false. So it can be a little bit confusing, but that is kind of how you can do, that's how you can do that. That's how you can do that. And so we can use, the reason why we want to do search, or the reason why I wanted to do search, is because that will allow me to more easily not have to incorporate this logic in, this is good logic that doesn't have to now be incorporated into the insert, because we gotta, we're gonna basically check to see if something is there or not. So we're gonna basically use the search function to say, hey, are you here? Are you not here? If you're here, if you're not there, then I can just go ahead and insert you. But if you are, two things. One, for this linked list, for hash tables to work this way, every value that is in this linked list must be unique. And so we are checking for that. We're checking for uniqueness with this as well. So we can check to see if something already exists in there, and we can kind of stop it all if it does exist. But if not, we can go ahead and stick it in at the head node of this linked list, and that will work just fine. And so that is why I wanted to implement the search functionality here. And then we can actually just use that search method to be able to do some cool stuff on the insert. And so actually, that's why I set this up right here, which I was on the right track, but I don't actually need to do that. Sims Life, we are not learning that right now. I need to update it. I never remember to update it. We are learning how to do hash tables. We're learning how to implement a hash table inside of Go right now. That is, we're building on top of what we learned on Tuesday with our linked list and adding to this. All right, let's see if we can get done pretty quickly here. So our insert now that we already have our search, we can utilize our search now to do this stuff. So we can say if, we can use a couple different ways. We can check for the value of something before inserting it, or we can insert it. So if it exists, so we can say if it doesn't exist, I guess we want to check if it doesn't exist. The bang flips it And we're gonna say if it doesn't exist, and so we're gonna say node bucket dot search, because search already exists here. Or not search, but whatever we call the search bucket. Come on, what's happening here? Search bucket. So we're gonna run the search bucket on here, and we're gonna test for the value. So as long as this doesn't exist, we're gonna go ahead and insert this thing into where we want to have this thing in it. So we want, let's save a spot for the new node that we're gonna be creating. We can call it whatever we want, but this is gonna be the new node that exists inside of this thing. And this new node, we're gonna save the value of node bucket, of node, let's see, the bucket node that we need here. What are we trying to change this to? I'm trying to think of the value. We're trying to change this to a specific value. And I'm trying to think what it needs to be set to. What does it need to be set to? Node bucket, current node. Our new node needs to be set to the value. At least we need to grab the value of one of these things. Of node, I don't think it's node bucket. What is the current node? How do we know what the current node is? The current node has to be what does the node bucket have? Dot head. That seems wrong. Let me think about this a little bit more. When you set a new node, then we need to I'm just going through the structure. Then we need to do a new node dot next. So our node, it has to be of type node new node dot next, and we're gonna set that to the original node that was already there. And then, but in my mind, I can't think of what needs to be set. For some reason, I can't remember what needs to be set as the new node value. I'm gonna try a couple of different things here. The new node needs to be a pointer to the actual new node. And what is the new node being passed in? The new node being passed in is the node bucket value. Okay, bucket value. It's going to be so like I feel like it's supposed to be node bucket new node that next has to be an empty something maybe. So the new node that the dot next is going to be whatever the current so this is actually going to be new node dot next is actually going to be the current head node before I change the head node. So it's actually going to be whatever the current head for node bucket is right now. It's going to be this. That's what the next, the pointer is going to be pointed at whatever the current head node is. It's going to be pointed at that. And then we're going to change the head node. So then we will then take this node.bucket.head, and then we will actually change, actually this is not, I don't need that. We will actually change the head value to the new node that we grabbed up here. This is the paradigm of adding an item to the linked list. But I think because the linked list is inside of an array, I'm trying to figure out how to specify. I'm a little bit confused on how to specify the actual array here. The actual thing that we need. So the new node is going to be a node that is in a bucket. I think we're gonna, I think we're gonna have to create it here. create the new node by doing we're actually gonna have to create a node. I think we're gonna have to create a node. Like, I think that's why I'm confused. I think we're gonna have to create the node like this, lowercase node. Where was I think we're gonna have to do ampersand node. We're gonna have to actually create a node that has a key value or not a key value, a value of whatever we just passed in. That feels okay. I think that is right. And so we'll test this in a second and we'll see what this does. We're probably gonna have to change a lot of stuff, but I think this is very close to what we need. Yeah, so it's gonna check. It's gonna use our search function. It's gonna use our search bucket function. Our search bucket function is gonna say, hey, are you inside of this bucket? Like, I'm gonna take a bucket. Are you inside of this bucket? And the insert bucket is going to use that to say, hey, do you exist there? Because if you already exist, I cannot insert you at all. And if it does not exist, which is what the exclamation point does, it is going to set a new node value. The new node that we're going to be adding is what we create. So we're going to create a brand new node with the value that's being passed in, with the string that's being passed in. We're going to change the pointer for the node to the current head, and then we're going to change the current head to the new node. And this feels right. I'm not sure it's right, but it feels pretty correct. And then after we implement this piece of it, we need to say, so we have an if here, and we need to implement an else because we have this, we're not supposed to do anything if it doesn't, if it's not in here. So we'll implement an else, and we'll basically just say format. We can do a funct dot, what do we want to do? A printf. And we want to say %v is already in the list. Let's try that, comma, and we'll make that value. All right, so I hope this works, and we'll do this. And we're actually just going to go hard and try to implement all the things really quick because all these are kind of needed to work together. We could have done some magic to do them separately, but everything is working. Everything's going to be okay. And we'll probably have to run through the, when you write this much code without testing, we're probably going to have to go through and fix a bunch of little things. But I'm hoping it's going to be all syntactic rather than, or like just, missing thing here, missing thing there, rather than any of the functionality. But we can take a long look at it in a second. So these were the two methods that we needed. The insert and the search are what we implemented for the bucket. Now all we got to do is implement the search for the table itself. So we already implemented the insert for the table. So we have one more thing left. We have one more thing, and it's very simple in comparison. Everything that is on the array itself, on the table itself, is actually pretty easy for us to do. And we need to do the same thing here. We need to do the index as we did above. We need to go ahead and hash this value for search. Why do we need to do this? What is it that we're actually doing? We need to remember, when you pass in the same value, you should always get out the same thing when you pass it in. And so this will give us the same hash value that we can use to search off of. Now what we can do is, this is the important piece of a hash table actually, is that we get the value, we get the index of where this of the bucket that this thing should exist in, if it does in fact exist. And then we do the same thing that we did above here, dot array index. And then instead of insert to bucket, we are simply going to use the search one instead. So, pretty simple. We're going to use the search bucket instead. And we're going to search for that value. Okay, a lot of stuff here. This is why I didn't want to introduce the delete yet, because the delete adds a little bit of complexity into this. But the table methods are pretty small. And the bucket methods aren't crazy small, but they are, you know, they aren't wild either. So we have a bunch of different pieces here. Now all we need to do now is set up our main function to hopefully grab some stuff. So how can we do this? So we're initiating a table here. We still need to initiate a table. We need to try to insert some stuff. So let's start trying to test each of these things individually. If we test, because both of our table functions or table methods are using the bucket methods, we really only have to like test like an insert or the search or the insert to get what we need. Yeah, that's all we gotta do. So let's test this out really quick. So to do this, we do the table here. Let's try an insert really quick on this. So let's do an R table dot insert table, and we need, what does that take? That takes an integer. So let's, you know, gotta pass in my name. And let's just do one. We only need to do one. We don't need this hash here. And let's see what kind of errors we get when we do this. All right, go return an error, and we got a bunch here. So let's run through all of them. Main cam froze. Okay, second time this happened today. Thank you very much. 4K camera. Let's change it to, you guys want to see a little bit of Inception really quick? What if I do this? Yeah, there you go. Now you can see in my face, you can actually see the iPad instead. You know, that's magic. I'm not sure why that happens though. I need to check. I need to look into why that happens. All right, we fixed it. We definitely fixed it. All right, so we got a lot of things here, but this, you know, syntax errors are what I was expecting. So line 41, 42, 52, 53, 54, 55. Now they all might be cascading. Expected close quote on line 41. So let's start there. Let's start on line 41. And let's see if we can run through. Bucket open closed if not no bucket search. Oh, I gotta close this. All right, so I think that's one. I think that is one. I had to close the parentheses here. Excellent. All right, so that might have fixed everything. I saved it. Okay, all right. We didn't have any actually go thumped errors, which is nice. Off of one, we missed one parenthesis there. Invalid operation current node equals value mismatch types node and string. Okay, line 54. Let's check that out. R in the table, undefined type hash table, no field. Okay, so let's check out line 54 first. It's saying current node equals value. These are two different types. So let's take a look at that. Line 54. So two different types here. I think that that's going to mean we may need to do like a current node dot a current node dot value. I think that's what we're gonna have to do is a current node dot value, because instead of it's current node is type node, but we need to check that key, that value, and so I think that's what we're gonna have to do here. So I'm gonna save that and see what happens. All right, we resolved that, or at least Go thinks we resolved that. And our last thing is line 88. Undefined type hash table has no field or method init table. All right, and so that's line 88. Init table. Did we change our oh, this is the wrong function. It's supposed to be insert table is what we want instead of init table. All right, I think that'll solve it. Phenomenal. That appears to have worked, but I mean, so the program runs. That doesn't appear to have worked, but it appears to have run. We need to be able to look at this. So how do we know that this inserted to the table? How can we check that? First off, I'm very excited that this ran. We inserted Aaron. Let's insert a bunch of things actually. Yank. And actually, this is a terrible way to do this. This is not, don't do things this way. We'll do what we tried to do yesterday, or the day before that caused a bunch of problems, but we'll simply, set up, names. We'll set up a list of names, make it pretty easy on ourselves. So a list of strings, and we'll set it up as Aaron, David, let's say Sarah. I always used to say, I grab the first thing that come to mind. Tim, let's see, Ruth, and Lydia. Don't know where those came from, but we'll set that up like this, and then we'll just do a little function so that we can just keep adding names to this if we want to do something else. Hey Todd Libby, how you doing? We are just trying to wrap up learning hash tables here. This is like my second time in implementing them in Go. So we're just trying to figure this out real quick. We are at the very end. We're actually testing. Somehow we wrote a bunch of code. We wrote 3 of the methods without testing, and it ran with just adding, like a parenthesis here and a changed object somewhere else, and it ran. So I'm pretty surprised. And now we're just trying to confirm it works. It's running, but now we're just trying to confirm that what we're looking for is actually doing something. So the way that we can do this piece is we can run for the items that are in for the names, or name that's in range names. We can go ahead and we can run the same thing that we ran to insert these. So our table dot insert the name, and maybe we can do a little bit of magic here. So that one, this will run, but again, we're just gonna get name declared but not used. Oh, why did I do that? Name. How can we see these things? The way that we can see these things is, can I print? I think if I print F it, so I think it's because it's the memory address there. I think it's only going to show us the last item in each column. I should have thought about this part. Percent plus V, new line. Do I want a new line? That feels like I want a new line. Comma, our table. Let me see if this structures it properly or at all. So it calls it as an array. Let's see, I don't remember how to do this actually. How do you print go print pointer value? Let's see. Let's see, go function argument passes value. I'm gonna have to structure, I'm gonna have to do all this. This is frustrating because I think it's working. Percent P and C, yeah, I don't think that's gonna work, but I'm gonna try it. Yeah, it's just gonna give me the actual, like, I might have to pull out, you know what? Let me try this. Our table, because this is array, our table dot, oh, maybe I have to do our table dot array. Maybe I have to do that. No, man, let's try this. Let's see what happens. Okay, all right, this is good. 10 items in there. And then what happens if we pick one? Array dot let's just try 2. And instead of P, let's try, I feel like plus V does it though. Okay, all right, this is actually good. Nil. So real quick, let's do a oh yes, we wrote that other file. Let's the hash function file, so we can find out what some of these names are equal to. Is our array size still 10? It is still 10. So let's pass in hash Aaron with a capital A, I think is what we had. So we get the value, and if we know the value, then we know where to look. Go run hash function dot go, not go ton, go run hash function dot go 7. Okay, so if we go to hash table and we look at the 7th slot here, theoretically we should get at least one item, which should be Aaron. Oh well, it just gave us the head of the space. Can I do like a, what happens if I do this? I don't know. Isn't 7 past the end? No, there's 10. There's 10 of them. You're probably, oh, I see what you're thinking there. So the array is a fixed size. Arrays are fixed size. So the array gets built with 10 slots regardless. I only filled it with 7 items, or 1, 2, 3, 4, 5, 6. I only filled it with 7 items. But yeah, yep, it's not that's just us populating it. And then remember, each of these can have multiple things. I don't know how to see that pointer value. Let's see, printf %p, oh, star p. Maybe we'll try output. Oh no, that's the same output. Some struct type int 2 to a and ampersand a, print line ampersand a. Okay. No, results in, I don't know how to do I int but no go, so not really sure. Yeah, yeah, I'm not actually sure how to see this in Go. I didn't get this far. It started working for me before, and I was like, yeah, great. I'm pretty sure it's working, but I don't know how to. Oh, maybe I can. Write a print function how we did it in. 1 second. Let me. Can we do something like this? Like the list nodes. Iterate through. I'm gonna take this really quick and get let me see if this, let me try something like this really quick. No, not this is not what I want. I want this one. And let's see if we can stick this somewhere and modify it. Let's put it right under here, and let's say print me, and it's gonna take this is how you print stuff in the linked list. Never mind. That was dumb. But that is what we want to do, maybe. And the linked list that's passed in would be a bucket. So we're gonna pass in the 7th bucket. We'll pass in the 7th bucket. But it's actually of type not linked list. This is gonna be of type bucket node. Actually, what is it called? Yeah, we're gonna call it it's just bucket, not bucket node. All right, yeah, let's see if we can make this work really quick. So we'll try to pass in the actual bucket really quick. And the length is what we need. And so we'll just hard code the length really quick. Here we go. We'll hard code the length really quick. Just test equals, the length is 10, because we already know. Oh no, we actually don't know how many. We don't know how many are in here. But it should be fine regardless. Let's put 6. I don't think there's not more than 6. There's like 2. And while test, this is sloppy. But I really don't know how to print this, which is really annoying. I need to learn this in Go. And we'll change this to test minus minus. Test, and okay, format.println. We're gonna be printing print me equals bucket. Oh yeah, no, that was right. I can leave everything as is. Yeah, my list.hid, so that'll take my list.hid. And next element though needs to just be next, because that's what we called it here. And down at the bottom, we will try to we'll insert everything, and then we will try to run print me, and in it we have to pass in an actual bucket. So we're gonna say our table dot hold on, our table and then dot array. Yeah, this actually might work. I'm gonna be pretty happy if this works. Our table dot array, and then we know we're looking for the 7th spot, and that will pass in a bucket, which is a linked list. That thing prints out what's in a linked list. And yeah, we'll actually delete this one for now. Actually undo. Let's actually just comment this out in case we need to. Print me.data undefined type node has no filter method. Oh, it's value. What line was that? Line 70. What? Oh, this is the wrong file. Line 70, and this is called list nodes, not print me. So list nodes, and print me.data is actually print me.value. And to the bottom, and this should actually be list nodes. All right, this feels better. Undefined list nodes, line 106. Okay, let's look at that again. What? Wrong file. Why is it list nodes? What do we call it? Oh, it's a function on, hold on, func. It has to be func my list bucket. That should work. Oh, because it's not a function like this. It is a our table dot list nodes. Here we go. Maybe dot list nodes. It's a method. Come on. Oh. Hold on. Oh, look at that. Oh, hold on. So it is working. We knew that Aaron was in the 7th bucket. It's the only thing that's in the 7th one. And so it actually did run, but then it tried to go to a spot that didn't exist in the, it tried to get to a point that did not exist. Oh my gosh. My camera must be overheating or something. But it did work. It worked. Hold on. You need to see my excitement. You 100% need to see my excitement. And I'm gonna need this to start freezing in more flattering moments. So you can see here that Aaron is the first thing that did it, but remember, we weren't able to know, we're not keeping track of the length. So because we're not keeping track of the length, I didn't know how far the stuff is, and we're not gonna keep track of the length because we don't know how much is in each bucket. But it did in fact print out, cause I told it to go 6 times, whatever. It printed out my name. Why is it opening up this file? This is not the last thing I modified. Whatever. But here's what we can do. Give me any word. Someone give me a very long word. Yes, give me a very any word. Just type it in and we'll grab it. Could abort the loop when it hits nil in the linked list. Yeah, we try that. Let's try that really quick. Oh, when .next is nil. Yeah, you're right. You're right. For the print me. For the list nodes, I could have it run forever, but here, just so I don't have to change up all of it, I'm gonna make it even jankier, and I'm gonna say if actually, I can actually just change this, not even to a 4. I can just say print me .next equals print me .next, and then I can say down here actually, this is extra sloppy, if print me equals I don't know that it'll be nil though, but yeah, sure. Is break a keyword in here? I don't know what language I'm in right now. Let's see if that works. I don't know if it works, but let's see. Of course, in it that way, but yeah, let's see. Abort the loop. Yeah. Yep, I was just trying to get the fastest thing. I just grabbed what we had, but this in fact did work. So Aaron works. Did anyone give me a word that I could use? I need any. Oh, there we go. Nebuchadnezzar. So here we go. First off, I need to get into, actually in 2 seconds, can you send, it's very funny because I'm the only one, I've said Nebuchadnezzar like 9 times to people thinking they would get the reference, and they never get it. It's really annoying. Can you send Nebuchadnezzar one more time? Because I don't want to type it in because I'm going to misspell it. Can you just copy and paste it? I appreciate that, some coding guy. I really do appreciate that. It does look like it's working. We're gonna remove some stuff and clean it up and push it up to GitHub in a second. But all right, Nebuchadnezzar. How can we confirm? How do we know which block Nebuchadnezzar is gonna be in? We know because we can stick it in here. What's it? C inside and paste this in. All right, so this will give us Nebuchadnezzar. Go run hash function.go, and okay, so it'll actually be in the very, Nebuchadnezzar will actually be in the very first column. It'll get stuck right in the very first object, very first array block, and so let's go ahead and let's pass that in to our hash table. Let's get all the way down here. Let's pass in Nebuchadnezzar. All right, and so it should be in the very first spot. So I'm gonna say our table. Let's look in the very first spot. Let's list everything in the bucket that's in the first slot, and we are going to go run hash table, and we do get it. And let's do one more thing just to make sure we're doing what we need to do, to make sure it's not just oh, this was the first option anyway. Let's actually move Nebuchadnezzar to the end, or like in the middle or something. Just let's also think of one more thing that's going to be in the first slot. I'll do a little math real quick, and we'll get one more string that will exist. We're dividing by 10, so it needs to be something that this, make it easy. What is JO? Cool, let's try JO. And also, what is a 100? What is an Ascii table? What is 100? Because we can just add a bunch of those. D, cool. Let's do it. Lowercase d. Oh, lowercase Joe. All right, I'll try that. I'll try lowercase Joe, and we'll just do a bunch of D's. Now, lots of jokes there, but PG stream, okay? The PG stream. So let's save this. So we should get all three of these back. Nebuchadnezzar, we know, is in the first slot. I guess Joe should be there too. I didn't do any math on that, but the D is 100, and so that should give us back, divided by 10, should give us back a remainder of 0. And so let's see if we get it. Okay, we got 2. So I didn't do the math on lowercase j and lowercase o. Lowercase j is 106 and o is 111, so that wouldn't work. That's going to give us 217. So it's not going to work, but we did get that. And so we can do, let's do n, and let's do 110, let's do 40, and let's do 50. So 110, oh, actually I think that's too low. I think 40 and 50 are not, well, I could put those in there anyway. Let's do more even numbers. Capital P, capital P, capital P, capital P, wait, hold on, let me see. Let's see. 80 times 4 will give us 300. Oh no, because that's dumb. Because now if I do one more, then that's even. So 5 capital P's will also do that. So let's do that as well. Just for, you know, just to confirm, you know, get 3 different things in there. 5 capital P's in here. We'll also put it in the very first slot. 1, 2, 3, 4, 5. Oh no, runtime error. Oh, I didn't put a comma. That makes sense. See, I catch my mistakes. I make so many mistakes that, like, I've stopped taking all the time in the world to, like, make sure they're right, because I'm still gonna make one, and I let the errors guide me. That's one of the reasons why I like Go. It tells me exactly what's wrong. Tells me exactly what's wrong. And now look at that. All 3 are in the first slot. Why are they in the first slot? Because they're all evenly divisible by 10. And so it sticks them in the proper bucket. This is good. It works. I'm actually surprised it works. Yeah, I'm actually kind of surprised it works. So what did we learn tonight? What we did learn tonight is that hash tables are a data structure that you can use to help you more quickly find an item in an array, especially when arrays get super long. Yes, absolutely, we can traverse through them. Absolutely, we can step through, but that's going to make our time, it's going to make it constant. It's going to, you know, if it's really long, it's going to take longer for us to get to the end. And hash tables give us a way of using a function, a hash function, to be able to determine where in that array, the exact place that something is located. And using that hash function, we can, you know, find out where to put it, and we can find out where to retrieve it from. And so instead of having to iterate through the whole thing, we can do that. We also learned there are 2 ways of resolving conflicts. So 2 things going into that, 2 different values, or different values that go into that hash function can actually have different, can actually have the same output value. So different things going in can actually come out the same, and that's a problem. So we have to resolve those conflicts. We have to do some conflict resolution. We have to do some collisions. Yes, and so we didn't do open addressing. What we just implemented, the reason why we were able to get these 3 things is because we did chained, I forget it, we did buckets. We did chained something, whatever, I forgot the word. Let me look on the iPad again. Actually, no, I have them in my notes somewhere on the computer. Yes, chain separation. Thank you again. Chain separation is what we just used. We did not do open addressing. Why didn't we do open addressing? Because open addressing works. Open addressing is when you find a collision, you check for that collision, you say, hey, is there something already here? And say, yes, there is something here, but I have something new that's supposed to go there. Then we just move over one. And, you know, we say, hey, is there something here? And if there's not, we go ahead and stick that thing there. That's really annoying. And that can cause problems. It also loses, you also can eventually, if you have enough items, you can lose the benefit of the hash table. So it does work. It definitely works. But where you get the benefit is with the chain separation, where you actually have linked lists inside of arrays. So you have an array, but each of the slots, each of the indexes of the array actually is a linked list, is a pointer to the head node of a linked list. And that way you can essentially stack, multiple things inside of a single array block. And so again, just super quick, it's like this. And right here, you would hold the pointer of the head of the linked list, and that way you could point to this node, and that node can point to another node, and that node can point to another node, and essentially you could traverse through these things when you needed to traverse through them. The way you doing that with the buckets, looking forward, backwards in the array is easy to bug. That's very fair. But yeah, yep, I will share this. I will put this on the actual site as soon as I figure out how to actually look at all of these. I don't know how to look through all of I keep adding new things to what's here, but I need to start using this more, and like actually use this application. But I will save this and attach this to the decoded site in Notion. If you want to see all the stuff here, I'm gonna save to a list, and open PDF maybe, and cancel. I don't know. I'll figure that out in a second. Let's push this up to GitHub really quick, because I don't think we have anything for all of these things. I don't think we ever pushed them up yet. What we did learn is that you can create these things from the command line with the GH tool. So I don't actually have to even leave the command line for this. And so what we'll do is we will get init. Oh, actually, I think I do have to, because I don't think I installed GH locally. Oh yeah, I did. Okay, cool. So GH repo create. And I think I just have to call it whatever I want. So we'll call this decoded data structures. We'll make it a public repo. This will create, sure. All right, so now if I do a git status, I'm gonna add all these things. Git commit -m added our data structure implementations. All right, I'm surprised that I'm not surprised, but I'm a little bit surprised. Usually when I write that much code without testing, it doesn't turn out that well. But it's okay. Sometimes you just, you gotta just swing away. Okay. I don't know if anyone's ever seen Signs, but sometimes you just must swing away. All right, so cool. I use the GH tool to be able to set up I don't know if anyone's ever used the GH tool, but I set up a whole repo from the command line using the GitHub command line tool. I just did GH repo create decoded data structures. And so now you all can actually get this from, I'll just click on it. And now look at all this. I push this code up normally as you do with Git. And now if you guys want to grab these implementations, simply grab them, play around with them. You make them better. For sure, make them better. We've just been doing them off the cuff, so I'm sure there's some optimization that can be had in all of these. But also if you just want a reference on how we did some of these things, you can hop in and see kind of what a queue or a stack might look like. I think we finished all of them last time. I can't really remember, to be honest, but that's it. It actually didn't go as long as I thought it might go. That's why we actually didn't have any slides, but I will attach the slides to either to both this repo and to the site. I'll stick them in here so that there's a PNG or PDF image in here along with this to kind of help out if you need help out with that. I also found a really good resource to someone else teaching these things in Python. And I think that's what I'm going to start doing, is giving you all resources for people doing implementations of the things that we do in other languages, because again, I think seeing it done in multiple ways like that can really help cement the concept itself. But that's it. That's all we have for tonight. Thanks for sticking around. We are back next week. What are we doing next week? I don't remember. Let's find out on Decoded. I think we're doing either sorting or searching. But we will be learning more data structures for those, but we'll be learning them as we're implementing like actual problems. So searching, we'll probably do we'll learn a couple different things through these processes. We'll do binary tree stuff, and we'll learn we'll learn a couple more types of data structures, but we'll do them in the framework of solving a problem. Then we'll dive into databases in 3 weeks, and then concurrent programming, whiteboarding, and have a cool little get to know some engineer session. If you're interested in any of the pipeline stuff, next week we're back with the DevOps and SRE stuff. We are doing all infrastructure as code stuff for the next 2 weeks. So Packer, lots of Terraform, a little tiny bit of Packer, lots of Terraform, possibly a lot of Ansible. I do want you all to learn CM tool, so probably Ansible as well. But that's it. That's all we're doing tonight. Who are we gonna head over to say hello to on Twitch? And as always, if you have someone you think we should raid, feel free to pass them over. I see Calo's on, I see Prime's on. Let me see. So let's see the two. Who haven't we seen in a while, or never at all? Who's on and what are they doing? Design and portfolio, modular synthesizer, JavaScript. I don't know. Cozy Coding. I think maybe we've rated Cozy Coding before, but we'll go ahead and say hello to Cozy Coding today. Let them know we said hello. Stick around for a while, but thanks everyone for another fun and exciting week. We'll be back next week, and have a great weekend. Appreciate that some coding guy, really do. Who are we gonna see? Cozy. I'm gonna go rest because I have to do some squats tomorrow and I'm not ready for it at all. But cool, let's go say hello to Cozy Coding. Peace out, everybody. Actually, I did that too fast, so we'll bring it back a little bit. Not peace out, everybody. We got to count it down. 5, 4, 3, 2, 1. Now I can say peace out, everybody, as I hit the button so that it's not an awkward pause. Peace.